Excellent. Good morning, all. Thank you very much for joining the second European Photon and Neutron EOSC Symposium on today, Tuesday, 26th of October. Just a couple of brief housekeeping slides before I hand you over to our host, Alan Ashton. So housekeeping-wise, please feel free to use the chat function should you have any technical issues, but please do not submit any questions in the chat. The questions should be submitted via the Q&A function, which you'll find at the bottom of your screen. And submit as many questions as you like at any time during the presentation, and we will answer those towards the end of the sessions. You have the option to upvote any questions being asked to give them more importance and rank them. And we will look to make the video and presentations available after our event. And lastly, just a reminder to say that the webinar is being recorded. Here's a brief overview of the agenda, which you can also access on our Indico page. And I will swiftly hand over to Dr. Ashton.
Right, good morning, everyone. So hopefully you can hear me okay. It gives me the pleasure to welcome you to this virtual second PaN EOSC Symposium. It's a shame we can't welcome you all to Switzerland, but unfortunately, when we made the decision as to whether or not we go virtual or actually have people on site, it was unclear how the situation would be with regards to the pandemic. So we hope to be able to welcome you to Switzerland as soon as possible. I wanted to just very briefly give some sort of context of the impact and the domain that PaNOSC and ExPaNDS has within Switzerland. We have a number of levels now in Switzerland regarding open research data. On the facility level, we have our own steering committee, which actually covers the whole PSI facility, which has the Swiss light source, Neutron and muon sources, as well as the Swiss FEL source. At the next level up, we have an ETH domain level initiative between a number of institutions with funding for projects probably starting next year, going through till 24. Switzerland is just publishing its national open research data strategy, and again there'll be hopefully some quite quick activity and funding in that. And we obviously take a pride in our relationship and our involvement in a number of international initiatives, whether or not it's domain initiatives such as the Nexus community, on the European level with ExPaNDS and obviously LEAPS, LENS, and going forward EOSC Future. And more widely on the RDA or on the international domain as well. So a number of activities that were important for us. And on the high performance side, well, the provision of computational resources, it's a little bit less mature than the open research data area, but we were in close collaboration with the Swiss Supercomputing Center to actually create a new initiative to actually have elastic on-demand resources available to PSI researchers and research communities. The project's already ongoing, but will be, again, probably mostly active from next year onwards. And again, in that context, we hope that we'll be able to offer our users and our communities, either through projects like ExPaNDS, additional resources and computational resources to be able to actually work on their data and their various initiatives. To highlight the importance of this area at the PSI level, there is a new scientific computing theory and data division that's been created, set up as only in July with 4 laboratories or departments. The laboratories are targeted more towards the research side of things, whether or not it's quantum computing, materials cloud, or various other simulation and modeling areas. But then my own department, which is Science IT infrastructure and services. We have a number of areas that we support in here, including the group now, which actually works on the ExPaNDS projects. We're responsible for the data chain, the software, storage, HPC provision, initiatives such as the Swiss light source upgrade, as well as various areas of communication, creating an SCD style community. The ExPaNDS activities are in the Data Analysis and Research Infrastructure Group and the newly created group, which is Scientific Data Curation. So again, an important area that's growing in our both in our facility as well as within the Swiss domain area. So that was in a nutshell, just a welcome from our side. We hope to be able to welcome you soon to PSI. So on behalf of Carlo, Chris, Valentina, who do most of the work within ExPaNDS, and then with Stefan, Leo, Miriam, who's still helping us in the background. We hope to be able to see you on site before long. Thank you very much.
Thank you very much.
I will stop my share as ordered.
Good. Hi, everyone, also from my side. I'm Sophie Servant. I'm the project manager of ExPaNDS, and I'll be sharing this morning until the break. So, yeah, I see Patrick, you've already shared your slides. That's perfect. So let me give the floor right now to Patrick Fuhrmann, our coordinator for ExPaNDS, who will provide us with the overview of both our projects. Go ahead, Patrick. Thank you.
Thank you, Sophie. Thank you very much. And let me join Ellen in welcoming you to this second symposium of PaNOSC and ExPaNDS. I'm very happy to have you all here this morning. And I made some notes before I forget. So first of all, many thanks to the local organizers and the organization committee for this meeting. They did a really great job, and they have been showing a lot of flexibility in moving online, face-to-face, online, face-to-face, and so forth. So in the end, we decided for online, as Ellen already elaborated on. Good. Secondly, thanks to the invited speakers. It's really a pleasure to have you here. First of all, the use cases. It's extremely important for us to see our results being used in science, and therefore it's important to have the use cases being presented here. Good. Secondly, of course, thanks to Robert, who is already with us, the chair of Lens, and in an hour or so, Katharina will join us too. It's important for us to have you with us because you are the hope we put into our future. Yeah. So thank you very much for looking into the survey that we presented, and I'm curious what your answers would be. Number three, or last but not least, thanks to everyone from the PaNOSC and ExPaNDS project. I know this has been a very hard year, but you did a very, very great job in contributing to our results. So this is very much appreciated. Maybe I didn't say that often enough, but I think Andy will agree that you really did a great job. So moving to the actual presentation, this is a shared presentation between Andy Gertz from ESRF, the PaNOSC coordinator, a person who really doesn't need an introduction anymore in this community, and myself being from DAISY and being the ExPaNDS coordinator. Yes, and of course, this presentation has been composed by a lot of people, not just us. Good. Before we really start, let me put our project into perspective. The correlate cooperation between the PaN community and the European Commission started already a decade ago with a lot of projects of benefit for both the scientists in Europe and the PaN community. So, and about 2015, there was a new kit on the block. It called itself the European Open Science Cloud, unfortunately. So let us focus on the open science in that term, because this is actually what all this is about. And then about 2019, ExPaNDS and PaNOSC came into life. But as I said, this is only one brick in the whole wall of open science in Europe. And as you know, and already mentioned by Alan, there is EOSC Future, which is taking results from us, from our project, into the future and making it available to other sciences as well. And there are more proposals coming. So we worked on a lot of things for the last 12 years. I come to this in a couple of minutes. Moving on. So just to make sure that you're talking about the same thing, our mantra is making PaN open science a reality by supporting our facilities in enabling fair data. Yeah. So there are various combinations of this sentence, but this is, from my perspective, the most important sentence of this presentation. Please keep this in mind. Good. So what does it mean? It has a lot of implications. They're all very technical. So we have to talk about things like Jupyter notebooks, portals, and we have to talk about something very obscure, which is ontologies. But putting this all together, there's already very positive outcome, as it will reported by our guests during the use cases. And there's something very particular where Andy is going to elaborate on. It's the human organ atlas. Good. So how do we achieve our goal? This is a kind of a layout of our two projects. It's very, very high level. So do not expect to get any details here, but this guides you through the rest of the presentation. So we have three pillars for those two projects. First, it's of course our research infrastructures, whether they are national or whether they are S3 doesn't really matter, because we are essentially working on the same thing. Then, in order to get all our science into the EOSC, which is one of our goals, we have to come up with rules. And this is what we call the FAIR activities. And rules are extremely important, because otherwise the results will be too diverse and will not be usable. So, and being German, I really believe in rules, as you can imagine. Good. So moving on. So what? Sorry. I'm sorry. Here we go. On the rules, we will talk about ontologies, as said. We will talk about catalogues, data set, the definition within Nexus, and we did a lot of consultation. This actually funneled into something which I will talk about in a minute. It's the bioportal. This helps us rendering the ontologies. Okay, so this is number one. And we hope that we get this bioportal into the EOSC portal as well. Good. So next up is all this has to be communicated to young people and has to be communicated to the beginners in our field. So, and we are doing this by having identified that a central training platform would be needed, training and learning platform. And so we are working on this, and this will hopefully end up in the EOSC portal as well. Next up is, it's essential to have metadata, otherwise the F in FAIR doesn't work. So we are working on metadata, on data, and we are working on making this available to the various portals with particular APIs we are working on. And last but not least, all this has to be run on some computers, and we need interfaces to those computers. And we are using batch, we are using notebooks, we are using Kubernetes, virtual machines, and so forth. And this has to be integrated as well. But we do not want to bother the scientists with all the bits and pieces and details. So we make this available through a kind of easy to use portal as well. And as one of the ideas is the cloud, we want to work in the cloud. Our services have to be portable. And in order to prove this, we are very happy that both projects have the EGI Federation on board. So EGI with the Fat Cloud can help us making our services portable. Good. This is that. Good. Now, moving to the results. Yeah, I'm sorry that I'm talking so fast, but I only got 25 minutes, and I want to get through this. Good. This is a little bit a table of content. It started being the results, the highlights of our projects. But as we go through all of those results, it doesn't make any sense to elaborate on this in detail. Now, again, in order to work on a common goal, as I said, for open data, for open science, we need to make sure that we are talking about the same thing. Yeah, and this is why we need policies. We need ontologies. So let me elaborate on this a little bit more. I'm using the high-level picture of the UNESCO on what it means, what open science means for them. Yeah, it's just a helpful tool. Good. Starting this on the left side, starting with data. I want to make sure that you understand what all those policies are about and why we need them. Good. Number one, we identify a certain set of elements which help us categorizing all the regulations we need in terms of making science open. So this can be the rights for the stakeholders, we shouldn't forget, retention policy, which means what is going to happen with our data in the future. We have to talk about embargo on licenses. We have to make sure the data is discoverable. And in the end, we have to assess whether or not we are fair. And we want to give help to our community, to our scientists on how to do that. When it comes to fair data, we even have to be a little bit more precise. Fair data, we identified a set of rules which we have to apply in order to make the data fair. So that is definitely global unique identifiers, not only for publications, but for data, for instruments, and for everything which is worth being permanent. Yeah, it's very important to understand. So second, we have to make metadata, we have to allow metadata to be conceptually understandable. Yeah, and this is where we come back to ontologies in a moment, because otherwise machines will not be able to understand our data. Second, we have to provide open access protocols, whether this is for data or for AI, doesn't matter. And as mentioned, our metadata needs to be machine readable. And we have to talk a little bit about standard file formats. Good. So I hope this gives you a little bit of an introduction in why we do all those regulations and all those policies. Now, what was our contribution to this? Yeah? First of all, we started with the data policies. Data policies are, when you are in contact with them the first time, not easy to understand. So what we did is we worked twofold. We have a framework for easy adoption. So if you have a small group and you're not really into this and your facility is not that big, you can just take it as a black box and you can apply this to your facility. Or if you are bigger, if you have multiple sciences at your laboratory, we provide a guidebook, and you take this guidebook and you compose and customize the bits and pieces for yourself. Yeah, good. So to compose a little bit more complex data policy. And then what we did is we didn't want to leave the facilities alone with that information. So we went to the facilities and we gave consultation, facility by facility, and we talked to them, explained what we mean, took their feedback, and kind of merged the feedback with the design of our guide. Good. And we didn't stop here. We will help the facilities in doing fair assessment. So is your beamline fair? Is your data fair? Is your reference data fair? And so forth. Good. Now, moving into ontologies. When I gave this a similar presentation at the LEAPS meeting last week, that really people were asking what is an ontology, but that's very simple. Ontology is the philosophy about existence. So as soon as you know that, everything is falling into place easily. No, that's just kidding. Good. So what we are using ontologies for is we want to connect things. Yeah, and we did this by you can do this on a piece of paper, but it's easier to have a tool. And as a tool to create those ontologies, we have been using the bioportal. The bioportal not only allows you to render your ontology, but it even gives you the ability to put this into contact with other sciences, which is very helpful for us. Our final goal is to put the portal into the European Open Science Cloud marketplace. So what is the result of the ontology discussion? Keywords. Yeah. So we want to make sure that we are all using the same keywords. Why? We are using those keywords, first of all, in the definition of the nexus file format, and at the same time in the definition of the metadata catalogues. So that when you have a keyword, this keyword can consistently be used to check the file, the nexus file and the catalogues. Good. What was our contribution? So we worked on the common ontology. So we checked the keywords for duplication, usefulness, and we had a survey if other sciences would understand our keywords. It's very important. We modeled the ontology into the bioportal, which was quite some work. We want to make the bioportal available in the EOSC marketplace. We are pushing hints for catalogs to pick the right keywords from the ontology. And as I said, we are working with the NIAC on the nexus definitions. Okay, good. Moving on. Moving to something which is very important because otherwise it's very difficult to find out what we actually did. So we have to have some kind of education. Good. So as I said, we found that there's a lack of a central platform for PaN teaching and for the PaN learning. And that was not identified by us, but by the facilities themselves. So they were actually asking for this. So what we did is we evaluated a little bit the state of the art of those technologies. And we used two different kind of platforms, one for the training and one for the learning. We reused two successful projects. The one is the Senior 2020 about neutrons, and the other one is the test platform from Alexia. Yeah, so we didn't want to do the work again. This is just a small look into our platform. So we are now online. So this is what you see in front of you is the training platform. It has certain categories, one of which is you can be linked to the PaN learning platform. And you would have to log in, and you have it's a kind of a Moodle, but it's more. Here you see all the providers we already have on board. It's quite an impressive number of facilities, and this is actually the training catalog itself. Important to mention is that we are not copying data from the facilities to make it available here, but what we do is we link to the original source of the data at the facilities, so that we are not forced to update our catalog every time they are changing something. Yeah, good. Last but not least, there will be a use case presented on the workflows in the platform by Jan Christoph, sorry, in the afternoon. Good. Moving to open access. Open access is a wide field. However, there is one prerequisite which everyone needs for open access. This is the identification of people. So this is called AI. Part of it is the authentication. Good. So some of you will remember how this was in the Middle Ages, I would say. At that time, whenever you wanted to use a service at another facility, what you would have to do, you would have to ask for an account at that facility. Yeah, this is really old-fashioned. So PSI had a better idea. They introduced the umbrella ID. Yeah, this was a big step forward. Fantastic. So you only need the identity of your facility plus one additional umbrella ID, which gave you access to all the other services at the other facilities. Good. But even that is no longer really state of the art. What we are now doing is, the goal is that you only need one identity. Because to be honest, you only have one identity. Yeah. So, and that identity is at your home facility. And that should be sufficient to access data and services at other facilities. It comes with many more advantages. It allows you single sign-on, and one service can automatically use a service at other facilities without even telling you, and it does it on your behalf. Two more advantages. All the legal issues of this are solved. So there is something which is called the ARC Blueprint, which is caring about the legal issues of services and IDPs in Europe. Not to forget, with this, we are part of a European-wide CERT system. It's an emergency system if there has been some break-ins. Good. And we are even moving this a step forward so that we are not an island in PaN, but we are part of a larger community of scientists in EOSC future. Okay. Pooh, that was a lot to learn. Good. Now moving on with open access. What I want to elaborate a little bit on is our idea how a PaN facility should look like in the future. So calling this, as people do, a next generation PaN facility. What you see in front of you is how a PaN facility looks like now. It's really oversimplified, but otherwise it doesn't fit on my slide. Okay, what you usually have is you have the metadata catalog, the proposal and people catalogs, the data, and the compute resources, very high level, and you make those available in various ways. What you, in any case, have is the proposal portal, yeah, because otherwise your facility is kind of worthless. Some have metadata portals. What you have is you give access to the compute resources, not so much by portals, but more through interfaces like the remote desktop, Slurm, and Jupyter notebooks. Okay, so this is how it looks like now. What we did is we added some kind of standards on top of it. This already happened last year. So we came up with a standard which allows higher level services to harvest your treasure, your data treasure, through the OI open archiving interface. And the second one for more detailed searches is something we worked on, which is the PaN search API, yeah, which allows you more than just the harvesting. Good. But we went a step further. So we worked on something which is called the Open Data Portal, which is, let me say, a reference implementation to use the PaN search API. This is something Andy is talking about a little bit more in detail in the afternoon. Sorry. And this is, of course, connected to the metadata catalog. Last but not least, you need remote access, and we would like to standardize this a little bit. So we picked the Visa portal from ILL, and this is adjusted to the needs of our facilities to give access to remote desktop, Slurm, Jupyter notebooks, and what you know. Good. This is what I would like to call the next generation PaN facility. And this is this depiction. We will use this picture to step through all those results we have very, very briefly. Starting with the open access interface, the open archiving interface. Our idea is, and this is already in place for a couple of our partners, is so those partners make this interface available, and what we get is institutions like a DataCite, you know, from the DOIs, B2Find from EODAT, and OpenAir as an EU project, Horizon 2020 project. They are able to harvest our treasures, our data links, actually the metadata, and they can make it available to a broader group of scientists. And this is already part of the European Open Science Cloud. Okay, so here we can make a checkbox that's achieved. Moving to a more detailed ability to search into our metadata. This is the search API and the Open Data Portal. The idea is here as well, similar to the harvesting interface, is that you can search our facilities, and what we want to do is to make this a federated service. So this layer I just drawn is it's more a virtual layer, is the PaN Open Data Repository. Yeah. So I want to mention that this can, of course, or will be customized to the needs of our customers. Yeah. So that could either be traditional publishers, there could be others for open data portals, and there could be others which are more focused on citizen science. Yeah. So the interface plus the implementation of the portal can be customized, as I said, to the needs of our customers. And as I said, there is a very nice example of this. It is the Open Data Portal customized for the Human Organ Atlas, but Andy is going to talk about this. I will skip this. This is the example of the data portal, but allow me to mention that here we see for the first time the advantage of having a proper ontology being used, because the techniques in this open data portal and in the API are clearly defined in the ontology, yeah, so that there is no misunderstanding, no ambiguities. Good. Skipping this because that's Andy's domain. Moving to a remote access. This is a big field, and I just want to mention some important parts here. So it is our goal to have the next generation of data analysis in a globalized research. Globalized means you need to have remote access to your facilities. You need to be interoperable. All your pipelines need to be able to move those to other facilities, and more importantly, even to what I call horizontal infrastructures. These are not facilities, but they are kind of the ability. These are actually the cloud. Yeah? So whenever you do not have enough compute resources at your facility, you can move into the cloud, and you can only do this if the pipelines are interoperable. Yeah, and for this, as I said, we picked the Visa portal, but there's a lot to do with the portal to make the portal able to interface your local facility. And for example, if you have a Jupyter notebook, what you want is you want to submit jobs into Slurm. So PaNOSC is providing one of those adapters which allows you to do that. Or some very neat tool is the Nexus HDF5 visualizer. You can run this either in a Jupyter Hub, or you can run this in your notebook. I'll have an example in a moment. Good, and together we are developing use cases for you guys. Good, and this is an example Andy provided. So this is a normal Jupyter Hub. What you can do, you can either directly start the application, which is the visualizer, or you can do this in your notebook. And this visualizer is quite nice. So it understands the Nexus content, and it is able to visualize this and it's highly configurable. It can do a lot of things, but I'm really not an expert here. But the reason I'm showing this is that this is now available through a portal. Yeah? So you don't need to have access to your facility directly, but it's all done for all scientists using a proper AAI. Good. That said, moving to our use cases. As I said, I'm very happy that we found those 6. There are many, many more use cases we are collecting, but those 6 will do for now. I don't want to go to all of them in detail because they will talk about the use cases themselves after my presentation. It's important to say that all of those use cases are picking a particular result of our projects. So whether this is the reusable infer or the interoperable infer, or the use of our simulation and the different work packages, or very importantly, as I said, Sun will talk about this, is this use case will show how important it is that you're using the right ontologies and you're mapping those ontologies in the file formats, because this only allows machine learning applications to run through your data without you telling the application how to interpret the entries. And there's more. There is one presentation about the PaN training, and a very interesting one on the Moonshot Consortium, which is looking for drugs to block the SARS-CoV-2. Good. So that was it from my side. Next up would be some use cases, and then Andy will follow with a presentation at 11:45 on the facility survey, and hopefully a great discussion on the consequences of the answer for the open data commons suggestion. But you will learn all the details from Andy later today. Good. That leaves me with thanking all of you for listening, and I hope you're enjoying the show today. Thank you, Sophie. Getting back to you.
Thank you, Patrick. Thank you very much. Okay, you have a question in the Q&A. I'll let you answer it if you are.
Wait.
No, I mean in writing. It's a bit technical, so it would take too long.
Okay.
And I would then give the floor to Peter to continue. Yes, good. You're already perfect. So Peter will talk about describing data by scripts for future reuse. He's a scientific researcher at the Charles University. Peter, the floor is yours.
Okay, hello everyone. Thanks for a nice introduction. As was said, my name is Peter Čermák, and I'm employed by Charles University. I'm working in Open Lab MGML, which is dealing with condensed matter. We have not so much time, so just jump directly into the topic. And as it was said, I will be dealing mainly with two last letters in the FAIR abbreviation. But let's try to test basically this FAIR if my own data which are opened are FAIR. So let's try to go through quickly if my data are findable. What to use? Let's try to use Google for that. And my data were on the cerium, gold, aluminum 3, and they were measured on triple axis. If I put this to the Google, this is my paper, this is my web page, and the fifth link is actually the link to the ILL data catalog. So you see the data are findable. It's possible to find them even by Google. Okay, I did some advertisement on Twitter, so maybe it's easier for this data set, but anyway, it's possible they are not hidden. Then I'm on this nice web page of the ILL data catalog where I can see the data description and also some parameters, and I can click download the data. And here comes actually some first problem. The data are hidden after authentication service. So I have the login, but this is, in my case, not super accessible. Even for the machine, it's a little bit complex. So I hope this will change with the PaNOSC and ExPaNDS in the future. But after the login, I'm able to access the data. So this is already possible. It's possible to find and access the data. But if I will look to the raw data here, if I will look to the one data file, you will see that it's actually quite complicated format. So formats are not standardized. This is not, I'm actually don't know if there will be sometime all the data formats standardized, but the problem with this data is that there is still a lot of information missing. How was the sample mounted? How to treat the data? Why we did actually this scan? So actually, if we want to treat our data, we will figure out that the data are findable, the data are accessible. What I'm adding is one more word. This is, I think, very important, that the data are trustworthy. This means that they are not uploaded to the internet by me, but they are automatically uploaded by the large infrastructure. So we can trust that nothing is missing. Actually, all the data are published. But actually, up to now, they are not interoperable and they are not reusable because we can't understand them. And this is a lot of work for me as a scientist to describe them. I will need to write very detailed logbook of what we measured. but actually there is an easy way how to do. And this I will show you on my idea, let's say, of how it should work in the future with the data publishing and the paper publishing. So what we have seen, where this raw data, this is this part, and this part is automatically published by the large research infrastructure, and this is already working for several infrastructures. And people are normally publishing the papers which are open, and they are citing the data. But this is not enough if you want to describe the papers, the data correctly and reproducibly. What you need to do is you need to use the scripts and not Excel or Origin. You need to use scripts for treating the data, and you need to publish these scripts. And the script should download the data from some raw data catalog, which is already existing. And then the script should calculate all the results and produce also all the figures for the published paper. And by that, you will actually describe the data, because anyone can then go through your scripts, and then they can redo your ideas, redo your research. It's also great for education of students and so on. So, and actually it has this very low cost, and it's actually possible to do it right now. So there is nothing actually missing. There is a lot of scripting languages. It's not only Python, but I will speak about Python, but it will work also in other languages. And I will show you the example how to correctly treat the data of this data from Hercules lab course in 2014, which was happening in ILL. First, our script needs to download the data. This is a pain, really, because we need to pass the authentication of ILL. So let's skip these commands. But after we will download the data, we can treat the data. And this is actually, for this data, very easy. This is some dispersion relation. So we are now here plotting the data. You see just few lines of Python code. And with another few lines of Python code, I can fit the data with two Gaussians, and I will get the position of my dispersion relation of the phonons in silicon crystal, actually. And with the last code, which I'm showing you, you can easily plot the results of this fit to the already known dispersion relation. So this is this mode, which was discovered during this Hercules lab course. And important here is this command, save figure. I'm saving this figure, and actually we will use this figure in the publication. So I have now IPython notebook, and for this IPython notebook, you can use easily also the PaNOSC services. So you don't need to run it on your own computer if your computation power is not enough, so which is great. And afterwards, actually, everyone who will run this IPython notebook will be able to reproduce all your data treatment. So you will describe the data by that. But will it work also much later? I think you all know the song by Zagre and Evans in the year 2525, and they are singing at the beginning, if the man is still alive, if women can survive, they may find, and of course what they may find our data. And what we should be what we now should do is that they will also understand the data if they will find them after 500 years. And actually this is possible because all the scripting languages has some kind of package index, a repository of all the softwares which Python can use. And if you will use some magic file, which is called requirements.txt, you will basically write all your packages which your script needs to have. And this same exists also in other scripting languages. And this is very simple format. So for this data, which I have shown you, you just need the 3 lines of code. And actually, I'm using just this for fitting. But what is very important is that you will specify exact version of the library which you are using. Because by that, also people after 500 years will be able to reuse it, because they will still look to the package index and find, okay, we will download this version from the year 2020. And if you have all of this, you will probably put your code to the GitHub, which is great for sharing and tracking changes. Actually, it's not very nice for citing. So it's nice then to freeze your GitHub repository somewhere to some Figshare or Zenodo repositories. This is just one click, and your GitHub repo will be then cloned basically to Figshare, and you will get a digital object identifier of it. So this is our GitHub repository of the files which I have shown you. And this is the clone of it on the Figshare, which has a DOI, so we can cite it. And there inside is some file, some IPython notebook, which is downloading data, treating data, and generating all the figures. there is this requirements.txt file, which is very important. So it can be used in 2525. And as a bonus, we added also all LaTeX files. So inside this repo is also the source of our paper. So everything is there. And after 1,000 years, it's possible to redo all the treatment and also generate the paper. And how to do it? If you don't need to actually install a lot of things. So there is a magic, let's say, service, which is called Binder. And this is already working. It's provided by Google. And actually, you just open mybinder.org. I will show you how that works. If you will look to our GitHub repository, there is this link, Launch Binder. If I click it, what is actually now happening? Okay, now it is happening. It's starting, it's creating somewhere in the cloud, some virtual machine. It's installing Python there, and it's downloading all the packages, exactly the versions which are in this requirements.txt. It will take some time, but afterwards I will load exactly my Jupyter notebook, and I will be able to redo all the treatment of the data by myself. So you see now it's loaded. It took just 10-15 seconds, and now I can redo all the scripts. I will not run them now because we don't have time, but finally I will generate the figures for my paper. So let's back to my presentation. With this, I'm going to the end of my short example of how I treat the data, and this is actually how to make your data fair just by publishing your scripts, which are fully downloading, fully treating, and fully generating all the figures which are then in the published paper. So all the presentation is for sure open, so you can find it on the Figshare under this link, or just use this QR code and the link for the data, scripts, and also the paper, which we did actually just in one day during the course, the mini school for people, for students last year, are available online. So thank you very much for your attention.
Thank you very much, Peter. That was great. A concrete example. And yeah, Google Binder, what we will add to this is resources from our facilities. So it's a very good example. Thank you. We have some minutes for questions. I don't think there is anyone raising his hand, but if someone wants to ask a question, please do. Otherwise, you can also use the Q&A, and Peter will, I hope, happily answer.
Definitely, yes.
Good. Yes, Andy, go ahead.
No, just a question to Petra is, do you link this example back to the data in the data portal? Are the DOIs linked in some way? Or, I mean, would this be useful? Yeah.
Yes, actually they are linked. If you will look to the data, but I think because it's not published, it's just on archive because it was just like an example paper. In the ILL data catalog, it's still saying it's not cited, but we are citing in this archive. So this is not so like link. Of course, if you will look to the README file in the GitHub repo, there are links to all the other scripts and so on. We also created a Docker image, so then it will also work.
Because it might, I think actually just a comment, maybe I think the system at ILL, which they use for finding its links, probably doesn't check GitHub. Yeah?
I think not exactly.
Yeah. But it would be a way, maybe if we gave you the option of just adding this, so someone else finds the data, will then find your repository as well. It'd be actually quite useful. No?
Yes, that will be a great function on all these data catalogs, that if I will be able to add links and also the citations. Yes.
Yeah.
Okay.
No, thank you. Great talk. Yeah.
Thank you. Fabio raised his hand. Fabio, you should be able to unmute now.
Yeah, hello, can you hear me?
Mm-hmm.
Yes.
Yeah. So a very nice presentation and a very good binder, fascinating binder example, I would say. But my question would be, from your point of view or prediction in the year 2525, how likely is it that all the packages are there in all the required versions? In other words, sometimes the reproducibility depends on details like exact version compliance, etc. in the PyPy packages, etc. How would you comment on that?
Yes, of course, this is a good question. up to now, it's still working, and people in these repositories are thinking about it, but for sure we cannot be like 100% sure. What is possible to do, it's possible easily, also it's on Binder written how to, because Binder is creating a Docker image, and it's possible to create this Docker image on your own and then store the whole computer image basically. And I really believe that even after 500 years, we will be able to run old Docker images, even if we will have different architecture of the PC. So this is probably the way, but of course one Docker image takes I don't know, several megabytes of there, but if you want to store anyway terabytes of data, then you don't care about storing the whole computer installation with you. So this is the way how to do it. Just the time was quite short, so I did not show you the way how to create a Docker image from your data, but it's documented on our GitHub. So it's not difficult, but if you don't trust that this, for example, PyPy will exist in 500 years, then it's possible to create an image of the PC, and this you can run, I think, always.
Okay, thanks.
Great, thank you very much. I suggest we go to the next talk, and if you can now stop sharing, thank you very much. And welcome Kamel Madi. Kamel is the co-founder and CEO of 3D Imagination, and he will present us a very interesting tomography case study. Hello, Kamel. The floor is yours.
Thank you, Sophie. Thank you, everyone. Sophie, can you hear me? Yeah? Yeah, perfect. So I'm going to share my screen. Okay. Can you see my slides here?
Yes, not yet.
Excellent. So I'm going to give you, so hi everyone, thank you to all the organizing committee for inviting me for this talk. I'm really grateful. I'm Kamel Madi, Director of 3D Imagination. Today I'd like to introduce you to the Athena software, which is a collaborative imaging platform for photon imaging data. So my presentation will be basically a quick, brief overview of what is Athena, and then I will give you a quick demo of a case study. So who are we? Well, 3D Imagination is a small company based in the Oxfordshire that has been built by two French people. So myself and Loïc Courtois, who couldn't make it today. And so we basically we are based in the Howell campus, which is, which I think you all know, which is a great campus to grow a business, and where we have access to some of the best facilities, including the Diamond Lightsource, the ISIS Neutron facility, STFC, and many more. And so our expertise is really on 3D and 4D imaging, but we focus specifically on X-ray computed tomography. And we are actually extensive users of synchrotron lab facilities, but mostly synchrotron facilities. So we go quite often to Soleil, ESRF, SLS, and Diamond Lightsource as well. Actually, we have a special relation with Diamond because we've been postdocs before, working with the University of Manchester, and based at the Diamond Lightsource, and so we were good users of I13 and I12 beamlines. So what we do basically is we do a lot of 3D, but mostly 4D dynamic processes, and we help companies and academics understand how materials behave and how to design better materials. So as you can imagine, we generate a huge amount of data over the year, and we at a faster rate, and we are essentially always facing problems such as how to access and share the data among the different partners following the FAIR data principles, how to visualize data coming from multiple imaging modalities, spatial, temporal, spectral, and many more. But also how do we analyze, how do we extract scientific information from this data, which is always a challenge, especially when you increase the dimension. So, so we at 3D Imagination, we really believe that a digital revolution is to happen, and it's actually happening now with the ExPaND and many more things that are happening in the field, in the scientific community, especially now with the COVID-19 situation, there's there's a real need to change the way we look at data. So the data just on its own is somehow useless, but if we put the data at the center of investigation through advanced digital platforms and software that we can access and share remotely, then data analysis will become much more efficient and much more quick. And that's exactly the idea behind the Athena software. So Athena software, so I will give you a demo just after this one, is a collaborative imaging platform that you can access and share remotely from any place, any location. In this platform, you can capture and trace the data and metadata without having to duplicate the data. And you can develop a workflow which involve all the steps that have been used to produce a publications. So sample prep, experimental protocol, the raw data, the visualization, right straight to the publication. Of course, the question is, what is the relation between Athena and ExPaNDS? Well, Athena supports the fair data principles, and there's a logical connection with ExPaNDS. One of the key strengths of ExPaNDS is to ensure that any research communities have access to both the raw data that has been collected at a given location and the corresponding publication that has been produced from this experiment or that is intended to be produced. So what we can imagine is basically at the end of ExPaNDS, an extra service where you can migrate this data and this metadata to Athena directly. And when you can start actually developing the whole workflow with all the steps that have been involved to produce this publication. Therefore, you can repeat the work that has been published, for example, and after some years, for example, or you can use the existing data to add another dimension to the project. For example, if you want to do some modeling, some machine learning, or use a technology that didn't exist when you did the project, or an expertise using another expertise from a different team. So we are actually working at the moment with the team at the Diamond Lighthouse, so Dr. Roberto Volpe and his team, and the team at the Diamond Lighthouse, who did a very nice piece of experiment on I-13 to study the biomass pyrolysis using fast tomography. And they want to understand actually the mechanisms behind particle shrinkage, which are very important for this application. So we are actually just starting this collaboration, and we intend to demonstrate how Athena can be used to enable remote data analysis, remote data visualization, and remote collaboration. So we will analyze this data and extract some very useful information and really show the whole method. So for today, I'm going to show you another case study which has been captured at Soleil at the T-shape beamline. So I'm just going now to move quickly to another screen. You see my screen, Sophie? Yeah, perfect. So this is the Athena platform. So it's a platform that you can access online from any PC or station or whatever. You need a login and a password. Once you log, this is basically where you end up. So you have a workspace in the middle, a kind of explorer at the left, and the data panel at the right. And here, for example, it's the Soleil case that we did. So this is the experiment where we use fast tomography using ping beam with our colleagues Andy King and Jean-Paul Ichier, and to study the solidification of a copper aluminum alloy. So we used a high temperature furnace to do that, and we were of course involved in the whole experiment. So when you click on the project, well, you can see here all the steps that we have created from the experimental protocol straight to the report at the end. So we haven't published this work yet because it was a proof of concept. But you can imagine that at the end here, we have a kind of publication. So the good thing is it's an easy to use platform. So for example, you can take any step of the workflow and you can drag it anywhere you want without having to duplicate the data. You can delete any step. You can rename the step of your workflow, and you can also change the status of the steps. So, for example, here you can move from in progress to completed, suspended, or failed. Once the whole project is finished after 3 years, for example, we hope that all the steps are activated. So what you can do as well is you can share the whole project and the whole data with anyone you want from the project. So you can add 3 different modes of access: you can be a viewer, an owner, or a collaborator. Whether you can view, edit, and the collaborator will have, for example, the right to do anything, including removing a user from the project, for example, or deleting the steps, or renaming everything. Now, in terms of the raw data and metadata, this is very important. So if you click now on the step, the raw data step, you have a series here of raw data that we have exported to Athena. And there is 2 ways you can import the data. You can do it manually, but you can also do it automatically using an automatic import service from an imaging equipment, for example, or software. So that means, for example, that you can directly link Athena to, say, for example, the beamline that has been used to collect the data. You can connect Athena to a CT facility or core imaging facility. And the way it works is, so this automatic import service is basically a program, a script that we call a watcher. And this watcher, inside, you can set the path of the incoming files. And the watcher will keep on looking at this folder, and whenever something is detected, a new file is coming, then it will be automatically uploaded to Athena at the location that you want to be. This is basically the user who decides that. Not only you can upload the data, but you can also upload the metadata, which is very important. For example, here, if I want to visualize this data properly, I need the dimensions of the image, and I need the type of the image, because it's a raw image. So, and you can also import automatically this information. Once you do that, if you click on the data here, which is a step on the given temperature, well, you can see at the bottom right, the metadata are already organized, and the data is loaded, and you end up in a viewer, which is the high performance viewer. And the good thing about this viewer is that you don't need a high performance or a very dedicated hardware. You don't need a very advanced hardware in your local computer. It's already embedded in Athena, and you can very easily visualize your volume in 3D. You can drag up and down, so it's a real viewer. It's not just a snapshot. There's a bunch of options. Not going to detail because it's going to take too much time. But basically, you can annotate the image. You can probe the pixels. You can clip your 3D image by your plane, for example, if you want to look inside in more details. It's quite nice. And while you're doing that, you can also instantly have a chat with your partners at the same time and start talking about the science and asking questions and really basically preparing the next step of the workflow, which is data analysis. So if I come back now to the workflow, something important about dynamic experiments. So we do a lot of dynamic experiments, like I said before. It's also how do we visualize time series. So having a bunch of raw data, for example, or an HDF file, whatever, where you have a lot of data embedded and looking at them one by one is not the best. So what we want to do is really, especially if you want to discuss properly the science and prepare for your publication and speed up the analysis as well, you want to have a look at the evolution of the morphological changes over time. So yeah, there's many ways you can do that. For example, the system of hyperstack, and this is something we want to embed in the future. But here what we did is just basically using a Python script where basically you can register all the data sets in 3D to remove the rigid body motion and then look at only one slice from multiple orientations. So for example, here, if I click on this data, it's a raw data, but actually it's like a movie. Basically, the slider, instead of having a slider that gives you the Z position, it's a slider that gives you the time. So yeah, so you see here, if I go up and down, I can see actually what is happening during the whole experiment. So I've got all the raw data from solidification, from the liquid up to the final solidified microstructure. So the reason I'm showing that is not only to show this, because I mean it's not something really wow, but what we want to embed in the future is basically also have the possibility to synchronize the metadata with the visualization. So imagine now I have a dialog box wherever in the data panel, and I can click on this dialog box. In this dialog box, I will have a list of metadata that I have pre-selected before. Of course, we're not going to include all the metadata because there are so many, but the most important ones. And the most important ones are those that are driving the experiments. For example, here it will be the temperature of the thermocouples. We can imagine here have this information. Also the information about the scanning settings. So we want to have the energy, the exposure time, for example, or any information that is useful. Why? Because imagine you have a set of data that is not reliable because the scanning settings were not stable. Why do you want to disregard this image? And the temperature is important here because if I can have this information displayed at the same time as I'm going through the slice, well, I can start looking at the science, really understanding what is happening, instead of doing that manually in a different software. So that was the time series visualization. Don't know how much time is left now, so yeah, I forgot to put my timer.
If you could be done soon, that would be great.
Yes. Okay. Yeah. So actually, I'm already finished, to be honest. I'm not going to detail all the steps, but the idea is really to show you that we can, at any step, we can add, we can capture all the data and metadata, all the analysis. So for example, here the segmentation recipe, we can have the schematic of the segmentation recipe, but also the script that has been used to segment the data. Then the binary volume can be used to repeat the analysis, but also to, for example, to add some modeling or some machine learning. And just to finish, the very last two steps here, speed measurement. This is something very interesting, not because of the science behind, but because this is something that we've done at the very end of the project. And we included a user who was an expert in solidification and who advised us actually to start looking as well at the local speed of the chips, of the dendrites, and actually for certain undercooling, the product of this velocity multiplied by the curvature of the dendrites is a constant. It's something that we verified actually, and it can be used to develop a model, validate a model. And I think I'm pretty much finished. There's a lot of things that we can do, but I think the real idea is really behind the data, metadata, the visualization, and the development of the workflow. Just want to come back now to my presentation and give you my contact details. So if you have any question, please contact me, and I will be happy to answer your questions.
Thank you very much, Cameron.
Thank you, and sorry if I took over.
Don't worry, that's very, very good. Don't worry. Yeah, it's good to see possible uses of open data and the need for metadata in commercial and professional services. So thanks for that. I don't see any hand raised. I'll give a few seconds if someone has a burning question. Otherwise, please use the, there's one in the
There is one in the Q&A.
Yeah, Stefan is asking if Athena is open source. Is Athena open source?
No, it's not open source. That's why when I described the product, I said you can imagine that Athena it's an extra service actually. It comes at the end of the. I imagine that ExPaNDS and the whole projects will be linked to different types of services that people may want to use to boost their research.
Thank you. Okay, well, if there is no one else right now, let me thank you, Kamal, and if you can stay a bit, if there are other questions in the Q&A, that would be great. Okay.
And if you could stop sharing your screen, please.
So that Musumi can continue. So our next speaker is Musumi from Eli Alps. She's a senior researcher, and she will talk to us about neutron diffraction from borocarbon for efficient structural analysis and defect detection. Musumi, whenever you're ready. I see your
I'm ready.
started.
I'm just trying to share my screen. Just a second, please. Do you see my whole screen there?
Yeah, in full screen, that's perfect. Thank you.
Yeah, great. So good morning, everyone. I will talk about neutron diffraction from borocarbon for efficient structural analysis and most importantly, defect detection. I'm from EOSC Szeged, Hungary, and I'm working in WP5 for now in PaNOSC and also will extend to WP8 later. Our user case is based on some work that we did in WP5 within PaNOSC. And before we go into that, I first want to give a special thanks to all my WP5 colleagues because it was done with all our integrated efforts. I mean, it's really the teamwork. So now, as you all know, for the PaNOSC project is about the calls and very important, like very efficient partners are involved, and ELI is one of them. As you know, Extreme Light Infrastructure, this is our institute where I work in Szeged, Hungary. That's for ultra short laser pulse and at high repetition rate. That's generation of ultra short laser pulses. There are, I mean, it's not only in Hungary, there are 3 ELI pillars, 2 others are in Prague and Romania. However, very important is like in each of them, as you know, they are user facility. So our main target is to support the whole efforts as an user facility for the user's experiment. So our case, user case, as you can see in PaNOSC webpage, all use cases, this is use case 18. Any questions later we can discuss because I would like to respect the timeline, time restrictions. So what makes a user experiment successful? As you know, that we start with some photon or neutron source, initial source, and then there is this propagation of the beam. So and then there is this light matter interaction or neutron matter interaction, whatever, the interaction with the matter, that takes a very crucial role. Then there is the signal and generation, followed by data management, data analysis, etc. Now, as you know, getting the beam time takes much time and effort. Finding optimal configuration of the processes and resources. If we can do that, then it reduces this time and like it makes the it makes the whole experiment much more efficient. So ensuring minimal idle time and maximal production can possibly be done with computational simulation, which is used for process analysis or process optimization. I will again come back to this, a summary in our summary slide. So talking about this interaction with material, which is a very core to any user experiment. So there, suppose if the material is shined with light laser, it is like it can change phase, or it can go, I mean, it can be in the same phase, but there can be different processes, physical processes involved. Like there can be molecular or atomic motions, control of chemical reactions, whatever are the processes. For example, this control of chemical reactions, that means to say motion of atoms or molecules, it's in a femtosecond process. Or if an electron is inside an atom and moving, that's an attosecond process. And often we in ELIABS, we address process, I mean, basic core processes and their applications in ELIABS. This is what we address often with this high intensity and high repetition rate lasers. Anyways, each of those materials can be described in one way or the other from the periodic table elements. So the core are from the periodic table elements. Each of the elements have their own nuclear descriptions, atomic positions, as well as their electronic cloud. So if we can describe the material well, then we partly solve many, I mean, the basic problem is partly solved. And then there comes this beam propagation and other things, as I mentioned. So what within this user case we are trying to do is combine atomistic simulation environment, or ASE platform, which uses density functional theory, or we are trying to add other as additional things, for example, time-dependent density functional theory. Later on, I will also try to add molecular dynamics and other perspectives. So that kind of atomistic simulation environment, combine it with another modeling tool, which is within WP5, which is, for example, called MaxTAS. It is this MUXTEST is often used for modeling complex optics using simple building blocks. Example represent a beam line. So I will show you very soon now. So this combination, using them, we are trying to create a unified interface, and within that interface, of course, that means to say it will be a modular code to mimic the beam line. CMEX is often used to mimic the laser beam lines, MUXTEST for neutron beam lines. So photon and neutron source, these terms are there in PaNOSC. So these are that's why they are the key pillars, CMEX, MUXTEST, okay? So this source beam line, this is how it will be, efficiently more mimicked, and the laser matter interaction part will be addressed with atomistic simulation environment. So how the thing works. So here within this use case, we chose a prototype system which is called borocarbon. Okay, because I am a materials scientist, I also have a tendency always to choose something that has application. So borocarbon has its conductive diamond with borons within the diamond network. That is for very highly efficient electrochemical detection, and it's often being used, a very latest material being often used. So this current use case combines EOSC and MUXTEST to create a common platform, as I told you. And very importantly, in the process, as you know, in EOSC, there are different codes that are being used. MUXTEST is being used for the beam line simulation. Now, the data output is, of course, based on used codes, it becomes different, right? So the goal will also be to unite the data format so that in a single data format, the user facility, they can access them. So that comes later, and then there comes the data management. Later on, we also plan, like whatever we simulate, we upload it in an open data platform where other users can download and benefit from the efforts already done. So the current use case action flow has the following steps. First is use ab initio tools to relax the geometry of the chosen material. Here it is borocarbon. So we have, using this ab initio code, we have their structural, elastic, and electronic properties. That means to say their ground state analysis is already done. We have, within this short time, we have not gone into this time-dependent density functional theory and these other things. So it is then using this relaxed geometries, they have the atomic positions. Those are essentially needed for MUXTEST, the neutron scattering simulation code for beam lines, and that is used to understand the different peaks in the neutron scattering signal. Note that as soon as there are defects in the system or some other problems, the peak positions will also naturally change. So I will show how to correlate. So that means to say among microatomistic features, there are manifold possibilities, and then we want to correlate it with the reproduced experimental macro features. So ab initio method, as very briefly how it works, we start with an initial atomic positions and then solve this whole loop self-consistently to get the effective useful potential, which will give us access to important output quantities, such as the final and realistic charge density distribution, forces, energies, and like that. So that way we have access to a structure, energetics. There are many available tools, Quantum Espresso, Octopus, VAST, Siesta, etc. For example, Quantum Espresso is already a part of this EOSC platform, and many others are. It's not a difficult task. So we are creating a Jupyter notebook that will support how to have those data accommodated within our platform. So for this current user case, the plan is like we have so we start with an initial structure. We have the relaxation. Then we go to the Quantum Espresso SCF output file. We have band DOS or electronic structures, as I mentioned, and using the same relaxed output data, that means to say atomic position, also run MUXTEST script to have your neutron scattering patterns. So now from the material simulations, you have the information of the materials, position of the bands, position of the defects, whereas from the neutron scattering patterns, you can identify which peak is originating from which defects or which kind of structure. So first, as I mentioned, for simulation of neutron scattering beamlines, we used MaxTas. These are the, I mean, if we visualize, these are different beamlines that they look like. For example, this is Vivaldi, ILL France, this is DMC Psi. So, I mean, I will not go into those details for now, but the output for those beamlines, how it looked like. So it's like pure C16 is pure diamond. You can see it is like that. As soon as we had 6.6% of boron doping within this diamond structure, we had some additional peaks coming into the picture, which are circled with red and blue. So now, as for different structures, as the boron or defect position changes or the concentration changes, the peak position also changes. That means to say, now suppose you have a material where which you are using in the beamline experiment. You have different peaks. What could be the origin? So some two experimentalists, they are both are using borocarbide system. What could be the origin of slightly different results? So that not only the defect concentration, but the defect location also plays a very crucial role. So this all needs to be very seriously taken into account while the synthesis or while the choice of the material for the experiment. So this is what it is. So that means to understand different peaks in the signal, depending on the sample, the defects, etc. Our approach helps to correlate with experimental features. So that means to say, if you have, suppose, a feature somewhere in the 90 degree, if you have multiple peaks like that, that means to say it originates from one of those boron defects, which was absent, like the other peaks, say example from 40 to 80, the other peaks, they were absent when it was just C16. If you compare, you will see. So now, why such combinatorial approach is important? So as I could probably stress that it is a combination of two different platforms, AAC or MaxTas. We combine and produce some experimentally relevant features. Why such approach is important? That here we are correlating atomic scale micro scenario among a manifold of possibilities, because defects could be in multiple places. Experimentally, it is very difficult to handle, but simulation-wise, it is much easier. So we can then tell that, okay, if this is the experimental macro features, it could possibly be this kind of atomic description or atomic distribution that is relevant or important for your system. This is the origin of those peaks. Similar, and this is more important, that it's not just MaxTas or AAC, but AAC plus CMAX, which we will maybe soon work on. That means to say this combinatorial approach, this analysis protocol, this can be envisioned for complete ultrafast laser beamline as in facilities like LE. And this approach is not only also LE, but it can support the user experiment and it has potential possibly for all EU laser or beamline facilities. So what do we achieve with such a start-to-end simulation platform, which we started with? So that we actually narrow the range of parameter space by saying that we have, like, suppose you have different photon sources that are possible, different pulse duration, repetition rate, profile, energy, beam wavelength, polarization. Photon propagation is another thing, different optics are involved. Photon matter interaction is such an important thing, like we just discussed. Sample description, it has its own electronic structure, atomic positions. These two we already just covered. Then, of course, there is signal generation and processing. So each of those factors, as you probably understand, like by having such a start-to-end simulation platform as we are attempting within WP5, we really narrow down the options for the experiment that, okay, probably this kind of pulse duration, this repetition it will be very important or useful for such an experiment. So that means to say, we kind of can help aid the experiment, investigating the feasibility of measuring signal. That means to say whether it makes sense at all. So we can probably help in that, informing the optimal design of the instrumentation for future experiment stations, probing physical understanding of the experiment, and so and so. So that means to say this can be considered as a virtual laboratory for optimization of user experiments. Very important is the last part also, that how much data is enough, because this whole thing produces lots of data. How much data? So this is where efficient scientific data management comes, and connecting to European Open Science Cloud is very important, because maybe some data is already there. We don't have to just store them once more. So, and also this open science is like, I have done something, some simulations or some experiments, another user should benefit. That's how it will help to move faster, make faster progress, right? So PaNOSC and ExPaNDS combined, their goal is that, and in reality, like there is another upcoming project, or like it's ongoing project, I should say, Impulse also correlates to that. So Impulse is another project, its main stress points are to develop joint management culture and capabilities of ELI facilities, which, I mean, ELI is where I work, as I mentioned, with an efficient use of resources. Identify opportunities for technical synergies to lower operation costs and increase availability for users. Scientifically optimize performance. So these are the very important thing within this project Impulse, which is integrated management and operations for user-based laser scientific excellence. However, I would also like to stress that this Impulse has 15 partners, 10 countries are involved. It's like a huge project. And very importantly, though Impulse focuses primarily on ELI, its results will impact all European high-power laser facilities. And with that, I would end my presentation. That was many thanks to my WP5 colleagues, my ELI colleagues, and for all the computation support that I received. To Theodore, Florian, Andy, and I forgot to add Nicoletta also. Thanks so much for trusting me with so much interesting aspects, and it's really overwhelming. I really love doing in this work, and thank you for all your attention. And I'll be happy to share any additional points or like being asked some questions. Thank you.
Thank you, Musumi. Thank you very much. Yeah, what you showed is at the crossroads of many things we're doing in the project. For questions, I would like to give time to Jan Christoph, so maybe we can do this writing, if you don't mind, and I will please ask you to stop sharing so that Jan Christoph can continue. So our next talk and the final talk of this session before the break is from Jan Christoph from HZDR. He's a scientist at the Institute of Radiation Physics, and he will be showing us the Telbe data analysis workflow and how he's using the PaN training platform for this. Jan Christoph, whenever you're ready.
Hello, everyone. Can you hear me?
Yes, we can hear you perfectly.
And can you see my screen now?
Not yet.
Not yet. Okay. Maybe now?
Yes.
Cool. That's good. So let me see if I can make the laser pointer work. Okay, you should have a pointer, right?
Yeah.
Yeah, so my name is Jan Deinert. I'm a scientist and co-leader of the Telbe terahertz facility in Dresden, and I would like to present you our data analysis workflow and some work on the PaN training platform that is done by our IT support, and then how this can interact and how we can kind of train users to understand better what we're actually doing, because this is quite a complex workflow. So first of all, yeah, we are the high field terahertz driven phenomena group. As I said, I'm co-leading the facility with Sergei Kovalev. We are a medium-sized group of experimental physicists doing both in-house research on accelerator research and development, because this is quite a young facility, which is not kind of finalized yet. And we're also looking at new materials, and our specialty is basically ultra-fast terahertz-driven dynamics and matter. And it's a user facility, so we do support the worldwide user community that's coming to us to do experiments there. what is TELBE exactly? So TELBE stands for Terahertz Facility at the ELBE Center for High Power Radiation Sources. ELBE is basically just an acronym for the accelerators. So this is a small accelerator, 2 modules driven by an SRF gun, and the TELBE facility sits right in the heart of the whole ELBE, producing terahertz radiation. So this is an actual image of the source. So there's 2 separate sources. One is in this small chamber. This is a so-called diffraction radiator, CDR source, giving us single cycle terahertz pulses. And the other source is basically where you have all these orange cooling pipes here. So this is an undulator, which generates a multi-cycle terahertz transient that's usually used to excite low energy dynamics in samples. So these sources are tunable. So here you see basically the typical tuning curve of the undulator source from the low terahertz regime to, well, below 1 terahertz up to, let's say, 2.5 terahertz at 3. Well, the energy is already quite low. As I said, the sources are twofold. There's the undulator multi-cycle source and the metal foil, the CDR, as a single cycle. It's all based on super radiant emission, so I won't talk about this too much, but just that you hear basically the keywords. What are we actually doing? How does an experiment look like? Well, we want to measure terahertz-driven dynamics on timescales that are shorter than the cycle of the terahertz. At 1 terahertz would be 1 picosecond, so we want femtosecond time resolution. With that, we excite the sample and then have a second laser pulse that's coming from a lab-based laser, which probes the state. So then we combine basically an accelerator-based source with tabletop sources in the lab. And what we're getting, this is just an example of so-called Higgs modes in superconductors, where we're looking at the response of the material in form of terahertz emission. And what you see here is, so basically this strong oscillation is the terahertz field that we're putting in. And then at some point, the sample itself begins to emit higher harmonics of this. And as I said, important is the high time resolution, so we can really phase resolve these dynamics, so we know exactly what the electric field at what point in time is, how the different phases are with respect to each other. And if we evaluate this, we can learn a lot about the materials that we're looking into. However, so this is not really straightforward. So since we're combining 2 very different light sources, tabletop lasers and a big accelerator structure, there is jitter both in time. So the delay shifts from pulse to pulse, and there's also slow drifts, and there's also an intensity jitter, which makes it difficult to reach femtosecond time resolution. And this is one of the kind of key basic features of our accelerator that we can compensate this, of our facility that we compensate this. So this is just an exemplary scan of many pulses where you see, and this is old, so the jitter is still quite strong now, it's a bit better, but where you see where intensity and timing of the accelerator is jittering. This is always with respect to the laser system. If you would directly measure this, a curve that I showed you with these oscillations looks completely smeared out. So the trick that we're doing is we're really measuring every single pulse, its time, or its timing actually, and its intensity, and then evaluate these timings after the measurement. So this would be raw data, 10 million data points, so measured over a few minutes. And then we can sort the data afterwards, and this is sorted data without averaging, so there's still a number of outliers, but if we do proper averaging, we arrive at these nice curves. We can actually sort also the data for different intensities if there's strong intensity fluctuations, and we arrive at a timing accuracy on the order of 10 femtosecond and get a pretty good dynamic range. And only with this, we can really do these ultra-fast experiments with sub-cycle temporal resolutions, which is now also employed at different accelerator-based photon sources. And we can also use detailed bunch diagnostics and learn something about the electron bunches and how to really optimize the source. Of course, if you're measuring all these features or these data at these high repetition rates, so we have quasi CW operation at 100 kilohertz, this produces tons of data. And the typical amount of data is a few terabytes per campaign. But you also need to understand basically how we produce this data, to resort our raw data and to analyze our data. And here's just basically a brief sketch of how we generate this data. Maybe I don't have enough time to explain it in detail, but this main method that we're using is the so-called spectral decoding technique, where we taking basically the temporal information and transform it or translate it into spectral information, so that we take for every shot a spectrum, and the features of the spectrum show us what the timing of the source relative to our lab laser system is. This way of operation is now running since about 5 years. Initially, measuring and sorting the data was very labor intensive and slow. So it took like half an hour after the measurements that you could look at your data. And with our IT, we worked on making this easier, and it's still not that easy. So this is, and I won't go through all the details, but this is kind of a minimal example. I don't know if you can see the site here. This is really the minimum information necessary to understand and reproduce the data sets that we are getting with. Here, basically our sources, source parameters. Here's our sample environment. There's the diagnostics, and here is basically all the computational infrastructure that we're using now to sort the data. So it took us a while, and helped by our IT department, to really integrate all these components and make it automatic. And for you to be able to understand it a bit better, I just show you basically a simplified scheme of this. So we have basically the experiment. The core of this is our data acquisition system, which is based on LabVIEW, and all the data goes to a network drive that's accessible by basically the whole IT infrastructure. And this is then analyzed automatically using self-written Python code. And this is running on our high-performance computing cluster. And when the data is analyzed, it's automatically synchronized with the electronic lab book that we have and put into a database so that the data is easily findable. By this, it becomes easy to basically chunk the functional units, and we're combining established tools and platforms with custom solutions. So Python, GitLab, OpenBIS is what runs our database. And finally, when the publication is there, or when we want to exchange data with our users, we use the Rossendorf data repository called Rodare. This integration and interlinking is really only possible by the strong IT support that we got. And further integration would require, I mean, it's of course not everything is integrated, not all sensors are speaking with each other. But there's already quite a high level of integration, so that the user gets their data quickly and that the documentation works fast. And what I skipped before, I mean, the goals that we have and that we reached in some ways or for some parts of our process is really get the recording automatic, assign the metadata automatic, get this data sorting after the measurement fast, and then make sharing and archiving the data easy, so that we're getting close to really the FAIR principle. And as I said, the IT department worked a lot on making this workflow happen, make our infrastructure speak to the database, to the HPC cluster, develop the code, etc., etc. The question now is, you saw that this is really a complicated workflow. So how can this be documented and maybe also published to share with others? And how can we train and inform our users about what we're actually doing to generate the data from all these terabytes of spectra and data from the detectors that we're having? And for this, there's now a project that has been started by Oliver Knödel and colleagues, which is the PaN training platform at HZDR, which uses this web-based interface to mimic or to kind of represent these complex workflows. And there's a first implementation of the data sorting process, which I would actually like to show you now. So how can I actually, okay, I can also just switch to the browser. I can just show it to you. So this platform, here it is. I guess you can see my browser, right?
Yep.
Okay. Yeah, so here you have this view. I'm now logged in, so I'm also able to edit things. I just show you that it's really kind of simple to edit this in the browser. You have these separate elements. So this is basically the process which is needed to get from the raw data that is, in this case, also published in our repository. So this is the paper that I showed you in the beginning. If you scroll down, you at some point get to this data availability statement that you see here. So you can directly click on this if you are just an interested scientist, and you get to the data repository where basically all these separate files are stored. There's also some metadata on how this was measured and how to interpret the data. So this would be basically single measurements. You see the size is already pretty large. And if you go back to the workflow, you see that the basic instrument to sort this data is a Jupyter notebook, which is in our internal HZDR repo. So I can just briefly walk through this or show you how this works. So this is basically explaining all the needed code written in Python to actually work with this data and to sort it. Just show you basically where you see the first results. So here in this interactive notebook, you can see basically, so this would be the timing signal that you get. Here's the raw data sorted for the first time. Then next step would be averaging, and here you arrive at this exemplary trace. And you can also automatically do some plotting, so basically do Fourier transforms and present this in different ways. So with the help of this training platform and with the software we're having, people can actually understand how from this large amounts of data that we have, we arrive at the spectra that we can show in a paper. As I said, this is not final, but all the basic elements are there. It would also be interesting to get in more data on how our facility works. So this is still work in progress, but this is really an interesting and really viable way to present this data and give not only our users, but basically the scientific community a way to understand how we work on our data and how a way to get their hands on this. So with that, I'm actually at the end of my presentation. Thank you very much for listening and for following, and I will be happy if you have any questions. And yeah, that's it.
Thank you very much, Jan. Just before letting you speak, Patrick, there's just a question in the Q&A from Sebastian, and I would invite you to go to the PaN training platform so you can find the link to the Jupyter notebooks. I'll provide it just after that. Yes, Patrick, please.
Okay, thank you, Sophie. Jan, Christoph, that was very, very interesting. And I hope we can visit you very, very soon and have a look how your installation really looks like. So my question is, as I said, I find it very important that people can understand how your system is set up, and it really seems to be complicated. But you as a deputy boss, did you put any procedure into place that whenever you change something, the documentation is following and that it is not out of date in a couple of months from
now? There's no like automatic procedure now. So that has to be implemented. However, the workflow at the moment is, at least how we gather the data and how it's uploaded, this is kind of fixed. And I mean, we're using basically the code that's on the GitHub to actually run our data sorting. So there is some feedback. However, this is of course not completely finalized, and then it would be good to have basically a really strong direct link. I mean, it's working pretty well here at HZDR, but to have kind of a constant link between the experiment and the IT. So there's, I mean, this is still kind of separate institutes, and the question is, yeah, how this could be organized better. However, yeah, I think for the future,
I thought you just had a solution, because I think all the facilities are suffering from the same problem here. Okay, thank you.
Okay, thank you. Thank you very much to all the speakers of this first session. We're running a bit late. I would suggest we still take 10-minute breaks. So come back at 20 past, and I'll let then Jordi chair the second session of this morning event. Thank you very much to all, especially to all speakers, and see you in 10 minutes, 8 minutes.
Okay, we are back after a 10 minutes break. We'll continue with the agenda as planned. So we'd have a couple more of use cases by Yusun and Professor Frank von Delft. And then we'll have Andy on one hand talking about a survey that we have done about outcomes of PaNOSC and ExPaNDS, and then we'll have talks from Lips and Lens to be finished with a wrap up and some questions and answers. So I propose to don't take any more time and go directly with Yu. Yu is a PhD student at the University of Szeged. I don't know if I pronounce it well, and is doing research at the European ExPaNDS, that is one of the partners of PaNOSC. So Yu, please share your screen. And you can start, you have 15 minutes, like for all the use cases and all our colleagues previously.
Okay, can you see my screen?
We can see your screen, but not in full screen mode. We can, and now, yes, perfect.
Okay, thank you. Thank you for the introduction and for the invitation of the talk. Today, I will present our use case of machine learning-based spectral classification. First of all, I would like to thank my supervisor, Sandra Brockhauser, and my collaborators, Christian and Susanna, for their cooperation and help. In this use case, we will show that how machine learning is applied for the big data analysis produced during the synchrotron experiment. Since the experiments in photoscience and synchrotron experiment will generate a large volume of data, such as the experiments of SDS, FXE at the European experiment. And it is crucial to analyze the data as it will reflect the status of the experiment on the investigation. And recently, the big data analysis based machine learning algorithm has become a trend, but machine learning will require the data to be clearly annotated and complete for covering the use and the reuse of the scientific aspect. And in this use case, we point out that the research hubs should align with the FAIR principle to facilitate the application of a machine learning algorithm or other data analysis task, and especially for data reuse, the metadata should follow scientific experiment data model, and it is also recommended that the appropriate nexus application should be defined. Our data is collected during HED experiment. Here we show example of data reuse, and the data is measured at the Petrol 3 at DAISY using 25.6 keV. The dataset consists of the 300 samples with each of 4,000 features. And during the HED experiment, the change of pressure will cause the change of spectral peaks, such as increasing, decreasing, and vanishing, shifting, splitting. And the major spectral changes we aim to capture in this study are the change of the intensity distribution of the peaks at certain locations, and also the shifts of the peaks. We aim to classify the spectra into two classes, which corresponding to the low pressure and the high pressure status of the system. And since the pressure value were not recorded directly with the raw data, we cannot automatically find the training set, but rather choose for representative diffraction spectral curves for our training dataset, and added some simulated ones to increase the robustness of our classification model. And here I show a nexus data file of our dataset. It can be seen from this file that the nexus-based class are used, but one problem is that the application definitions is not available. Only some free key values under the NX collections is listed. And another problem is no real experiment data is registered. For example, the beam energy, as I introduced before, the actual beam energy we used is 25.6 kV, but it shows it is not recorded correctly. The data we show here is one module of the 3-module detector system. And now I introduce our classification models. In this work, the classification task is regarded as a general two-dimensional space segmentation problem. As you can see, that the spectrum is overlapping in some regions, and overviews the classification of the spectrum of the data points is difficult and meaningless, as indicated by low classification accuracy and reliability. So considering this reason, we divided the spectra into several beams and apply a 2-layer neural network with the same structure to learn classification models. And the learned classification accuracy is used to indicate the local separability, and also for calculating the believability weighting factors according to this equation. And here we show the preliminary result of on the 18 beams, and the final classification level is calculated by a weighted sum of the pointwise classification result assigned by the neural network in each bin. And since there is no final choose of the phase transition point, we define classification confidence according to this equation to show how small this ambitious region is. The ambitious region is defined as the classification jumps inconsistently during the both phases, and to test and to decide the minimal number of bins to be used in the classification model. We also test its classification confidence on the different number of bins. It shows that with number of bins increase, the classification confidence is getting higher and higher, and the ambitious region is getting smaller and smaller. It shows that the bin weighting technique can minimize the misclassifications of the data points in the overlapping regions and makes the some distinguished features dominant. And in previous work, the weighting factor is calculated based on the classification accuracy, which is not an end-to-end solution. Here in this model, we extend the previous work to end-to-end structure by adding one more fully connected layer. In this way, the weighting factor can be automatically learned during the training. And here we show some results. You can see from this figure, with the increase of the number of bins, the trainable parameter increased linearly, and the training epochs decreased, and the training time also decreased, while the classification confidence increases. More generally, the spectral, the diffraction spectral can be regarded as a one-dimensional time series data. Under these settings, several other classification models can be developed, such as the convolution neural network, ResNet, STM, or state of the transformer-based solution, or other hybrid models. We just show some examples here. In conclusion, we have achieved a nice result on the machine learning-based classification, but as you can see, the process of selecting the training set is still very limited. We cannot select our training set automatically in the supervised learning because the data is not properly annotated. And it is difficult to use and reuse the data for further analysis without the help of relevant scientific experimental scientists. And so we recommended that appropriate nexus application definitions should be developed to help the setup of our machine learning models or other data analysis tasks. And the PaN portal is enabling the FAIR principle in data search, downloading, data analysis, and visualization, and also the automatic data interpretation. We expect the PaN portal to implement all the functions that we need during the machine learning analysis. Okay, thank you.
Thank you very much, Yu. That was a good presentation. And what I propose is that anyone that has any questions, use the Q&A section, and then either we will reply in line or at 1:45 with the planned questions and discussions to wrap up. And with this, I would like to say to you, please stop sharing your screen, so then our next speaker can prepare any slides, and is the Professor Bram Frank von Delft, that works as a beamline scientist for Diamond, but also at the University of Oxford. Frank, are you ready?
I am, yes. Can you hear me?
Yes, loud and clear.
Sorry, just trying to make my computer behave for a second. Getting there. Right.
Okay, perfect.
Can you see my slides?
Yes.
Excellent.
Please go ahead.
Thank you for the invite, and hope that this is useful. I just thought I'd quickly, or actually Isabel also asked me to talk through what we did during the pandemic, which we needed to be quite aggressive about getting data out. So it's an example of somewhere in between getting DOI set up, doing fair data for an experiment we did specifically to try and help the COVID effort. And the driver is that very early in the pandemic, we did a experiment, which is the facility I run at Diamond is called XChem. It's attached to a beamline, and we did an experiment which is generates starting points for drug discovery. And I'll say something briefly about the experiment by screening, testing one of the targets, one of the enzymes from the main protease. And so we generated these results that are essentially derived data very quickly. We were quite surprised how quickly it went. And then we tried to put it online for the non-specialist community. So people that aren't crystallographers, protein crystallographers, using a platform which we called Fregalis. That's like analysis, if you want, which we've been developing, and we use that to trigger a very big crowdsourced effort called the COVID Moonshot. You may have heard of it. So it was a crowdsourcing effort which we did because we couldn't mobilize funding to pursue this project. But very quickly after that, sorry, it got chopped off here. That's the view of the beamline, by the way, the beamline that I also run. And then we had requests from the specialist community to make the raw data public. It was a broad request because a lot of crystallographers were generating data, and we thought how to do it. And we had the data up in the public domain. So we're trying to figure out how to do that. So just the experiment, I'll very quickly talk through it. Essentially, I don't know if the video will work now. Maybe it won't. Oh, there we go. Let me just make it a bit faster because there isn't that much time. But what we have is a bunch of crystals that are protein crystals that grow in these plates, and then each of these crystals, those are diffract, and each of them one can add a compound, particular compound. They're called fragment compounds. They're just very small, so they bind very promiscuously. So we have this machine that will shoot them up with acoustic drops and scatter them. So soak the individual crystals. Each of these is now the same protein crystal with possibly some species bound, and then we have to pick them all up under the microscope and go and put them in liquid nitrogen. And these little pucks full of sample pins get put into the beamline, and the crystal up there gets exposed with the X-ray, and so we get a full diffraction data set from each of those crystals. And in this experiment, it was quite a large one. It wasn't infinitely large, but we had about 2,000 of these diffraction data sets. We had, of them, 80 of them had interesting species bound to them, and very rich metadata of the full data set. And this really needed to get out. And sorry, let me go on. So we published it in this platform I called Fregalis. There's quite a lot that is involved in getting that far. Even once you have the individual crystal structures, you have to essentially align all these protein structures to one another and give them some curation. And you have to check that there's no mistakes. This is a big step. And then we put them in Fregalis and also into repositories like the PDB. Now, the PDB, oh, I should say it's a lengthy experiment, lots of things involved, lots of different components, and it's been an ongoing challenge how to achieve all that to come out. But anyway, the formal repositories that have existed for a long time, essentially the first one is the PDB. This is a receptacle for the derived data, so the final data. It's been open. It's a place to put stuff in the open, and way back then in the 70s, the community was actually one of the leading communities for open data. Afterwards, later we had the genome efforts as well, but the PDB was, and the structural biology community was trend-setting for this. And so for the last 20 years, it hasn't been just the 3D coordinates of the proteins, but also the reduced data. So something that's not quite raw, but it's when you take the diffraction spots in the images, and you can extract them and get numbers attached to each of them. That's what we call the reduced data. But it allows reanalysis, and it has the most relevant data and metadata, and it's free to users. You can all go click on it. And about 20 years ago, the journals started requiring structures to be in the PDB. They all have these little codes, and there's 3 sites around the world that allow you to retrieve data. But we had this action for the raw data. So there's the data that came straight off the detector, so not the derived data. And that's much bigger. And so it was many terabytes of data, and also quite involved. And there were communities that were anxious to see that data as well. I suppose also hoping they could contribute to the global effort. So we decided to go with Zenodo because of having some familiarity with it. You can prepare up all your data in a sort of mail merge spreadsheet, and where certain things are involved. It all gets put into one big archive. I don't think it's zipped, it's maybe tarred and then zipped. So for deposition, you have this big pile that you can upload. And you can do it programmatically with an API that isn't published, but the developers were very useful. So Graham Winter at Diamond took it on himself. But actually, the main work was to get the metadata organized. I'm sure all of us have been there and recognized the problem. The raw data was in some subdirectory, and you could pile it together, but to attach it to metadata was needed a bunch of curation. I mean, the main work, apart from the programmatic aspect, but we didn't have this set up as a pipeline yet. And the other thing that had to happen was that Diamond's exec had to sign off on this route of deposition. It didn't object, but it just had to be made Diamond policy. Isabel and others just made sure that this got approved. So the data ended up in Zenodo, and there's a DOI for this. And then those structures had been in the PDB. So I didn't say that. So we had put all our 80 structures in the PDB alongside this publication in Frugalysis. And then we could just send all the DOIs to the PDB team. They updated the entries in the PDB, and then there's a link from the PDB to Zenodo. So if someone sees this, they can click on there, get to the Zenodo page, and get the data, so users can find it. So from the specialist user's perspective, what we achieved, quite a lot of it was not hacked, but done in some rush, and there was a lot of pressure. Of course, it was locked down and everything else, but it was entirely achievable once we decided to do it. So the data can now be downloaded, the raw data, and used with standard software. So the raw data is exactly the same as the stuff we used to process the data. There's no site file needed. So describing the diffraction experiment, that's all part of the deposition. Results can be produced. You can get from the PDB, you can get the final model, which is useful for reinterpreting the raw data. And so the users, if you like, the crystallographers think in terms of PDBs, but there's a persistent identifier for that now. There's no entry barriers. You can just upload stuff, and people are familiar with the format. So these data are now, I think, properly fair and accessible. But I'll make one more comment. So that was very nice to see using established infrastructure. But I think the key point here is about the specialist audience, and this does need thinking about hard, which is who are the audiences for the data. It's something I don't really think we're talking about enough when we talk about fair data. And the key point is this non-specialist specialist user. And for this experiment we do, so crystallography, or particularly this XChem experiment, our non-specialist audiences are actually chemists. They certainly don't tend to work with these 3D coordinates of proteins. They actually work in 2D. They draw little chemical structures. They definitely don't work with the raw data that come off the detector. So the number of people that care about that are very small. So this Frugalysis interface we've been developing is trying to cater to a non-specialist audience and put these derived data, these final high-quality data, straight in their faces so they can just interact with it. And that needs quite a lot of preparation on our side. So you have to first annotate and communicate the issues with the models, not even the raw data, but the models. So we've got that. We've been developing this over the last 18 months since this deposition. then you have to contextualize. You've got lots of independent diffraction experiments that collectively say something, and you have to contextualize that. And then you have to publish it to the world in a way that this can be interacted with. This interface actually is a 3D interactive interface. And finally, you've got this discussion opportunity where people can annotate things they see and put discussion threads and communicate with it. This is a very recent feature we've added, because we saw that this is crucial to actually make use of the data. And so what we then have is a web interface where people are interacting with the data rather than just accessing it. And that interaction turns out to be extremely powerful. And I do wonder how many of the other topics that we talk about when we think about ourselves as data scientists forget that the thing that makes the data powerful actually isn't the things we worry about, which is, you know, depositing and fair, everything else, but it's the conversations around the data that can be really transformative. And that's what we've been trying to do in Fragalysis, and maybe that's also an exemplar for how we should be thinking in the future. I should add that the fact that they are cloud-based technologies that can be readily deployed or engineered around the data has been crucial. So essentially the data now, let's call it the derived data, can be viewed, downloaded and annotated. And no pre-knowledge is needed at all. You can literally just click share and then copy a URL, and you'll see that 3D view of the data, which is the thing the person saw when they were annotating it. So that's quite powerful. So the data also can be fair, but the implementation is hard. One has to think very hard about it. It's not just about data science, it's about understanding the field. Anyway, I'm happy to show anybody around that if they want to. I should say that the outcome of this COVID moonshot, it's been quite successful. We got some funding that we were able to mobilize another 8 million to sort of take these compounds into preclinical tests, and maybe in a year's time, we may be able to enter the clinic just in time for the vaccines to fade and no longer have their power. So that's actually been a surprising outcome of making data public. And actually, the whole point of the effort was it should be a public effort, because in the end, we hope that this compound will be publicly, the way to make it will have no patents attached. And if the data hadn't been public at the beginning, this would not have happened. So I think making data fair obviously has a big impact if you do it right. That's all from me. I hope I wasn't running over.
No, it was perfect, actually. Thank you very much, Frank. And I think that now we can go with the next presentation. It will be by Andy, that is the coordinator of PaNOSC, works with me at the ESRF, and has some slides regarding the project's outcome and the adoption by the different facilities. So Andy, please.
Okay, can you hear me?
Yes, we can.
Thank you, and thank you, Frank. I was very interested in your talk. I would be interested to talk more. Is the solution open source?
I think open source is extremely powerful, but with a lot of work that is funded from not open source things.
Okay. Okay, so let me kick off. We're on time. I'll try and stick to that also, that we stay on time. And share my screen. No. This one. Yeah, so my job will be to present to you a survey, the results of a survey we did. Some of you have seen this already, but we will be talking a bit about a few other things. And I'd like to thank the LEAPS partners who replied to the survey, to Patrick, who gave his wise comments to improve things, and also, of course, to everyone who has contributed to this. As Patrick said, our mantra is really making data available and making sure it's one of our important KPIs is how much data have we made available over the course of the 4 years of this project. But now, seeing as we only have 1 year left, we thought it's important to project into the future and use this remaining year not only to finish what we promised to do, but to prepare the future as well. And this is what this talk is mainly about. We went to the LEAPS community and asked them for their how they see the outcomes of these two projects. But before we get there, I just wanted to show a little demo of what Patrick already hinted at, and also to show this very nice slide of our goal is to create a PaN data commons where we would be able to provide open data that's similar to what Frank has shown, but not only as something as, let's say, huge as Zenodo, which is a mixture of almost everything under the sun. This would be data from the Photon and Neutron sources available via what we developed as the search API, reading data from existing facilities and then making it available. And the example I wanted to show was the one that was already mentioned. I don't know if you see this. You see this, Jordi? So this is the Open Organ Atlas, which is data that is now just right this week is being made open access because the publication has come out in Nature Methods. And what you see here is we are using an example of using the PaNOSC search API with a bespoke or customized version of the search portal. So when you come in here, the idea is that you would have, similar to what we also saw in the previous talk, for a specific community interested only in this medical data, they would go to this site. But behind it are, of course, all the open data related to this kind of application. And they can go in there. So I'd like to really thank the people in my team, like Axel, Alex, and Marjolaine and Jerry, who helped make the site. Of course, the scientists did all the really hard work, which is preparing the data. But you can go and explore all of the different models here of things that people have actually, the patients that are in there. You can look at all of the data sets. You can go and download them individually or download them with Globus. You've got little movies which will show you things, I mean, so that you can view something which you could use. In the future, we could imagine having a better 3D viewer, but this is already a very interesting movie to watch. And finally, using the search API, you can go in there and say, I'm interested in only the samples which are of the heart, or I want only things which have a very small pixel size, for instance. So you can go down here. And this is where we're heading with the search API, is to be able to make these kind of choices, which are very adapted to the domain in which you are looking for data in. We still have some work to do, but now you can see this was to give you a feeling of what we actually want to offer. So if I go back to this slide here, you've seen the demo now, and our vision is to make this all the open data.
Andrew, we still have the website.
Oh, you still have the website.
Ah, no, now it's good.
Okay, so our vision is to create a common space where we can have these kind of either bespoke or generic front-end portal, which allows users or citizen scientists to search for data, download data, and of course, going in the FAIR concept or open science concept is going further to have all the associated input, like the notebooks, the workflows, any kind of training material. We saw that in the talk from HCDR. Of course, it has to be remotely accessible. Cloud is a must in this area, and also accessible via the EOSC. And that our users who sometimes don't come to the facilities anymore can also have access to these services during and before the experiment. And this is something which we see happening in the EOSC space. These are the other 5 big clusters that were financed as part of EOSC, and they are all developing similar things as well. So we thought, okay, we are on track with this. We're heading towards a successful outcome, at least the outcomes that we were envisaging from the beginning. But what about afterwards? Will our members, they say facilities, who are members of these 2 projects, and a large majority of them are represented by LEAPS as well as LENS, will they actually pick these up, and what will they do with these outcomes? So we posed these 3 questions to them at the beginning of the month, and we got a very nice set of answers, which you can see over here. And you see, this is, I mean, it depends again, this is a question of if you are an optimist or pessimist. This is a glass half full or half empty. If you look at this, it could be there's not a lot of green, or there's, you know, there are too many unknowns in here. But actually, if you look at this from, say, winding forward into the future, The results that we're looking at, by the way, I did get one lens partner replying, which was ILL. Well, that was because I also contacted them directly. And so we have one Neutron source in here as well, picking up these outcomes. If we wind forward, we see that actually there's a large majority of yeses, people who are accept, let's say, facilities saying that they will pick up the majority of the outcomes. And then the question is posed is how will we combine this all together into a common, let's say, portal. And this is what the question I would like to ask to the speakers who are going to follow after me. We also asked as a follow-on, as I showed you, the other two questions was, so we had 12 out of 16 saying yes, they subscribe to a common data commons. And then there were three scenarios offered, either a completely local solution or completely centralized, or completely, this is sort of like Zenodo, or completely, or a hybrid version of that. And we have a almost even split there of locally is fine for us, and that's probably because those are the ones that already have something in place. And then the hybrid ones was probably those who are saying, well, hybrid is maybe a good way to start because I don't have to set up all of this infrastructure. I think, you know, they're not exclusively, they're not mutually exclusive. The two scenarios could coexist. What we need is something, we need some commitment, which I'll come to afterwards. And then we said, do we need a common paper just to align all of our thoughts? And there was an overwhelming majority was yes, and only one no, but I didn't have a chance to speak to this facility to find out why it was no. So what would this cost? Well, with the different scenarios, I think from a cost point of view, let's say what management would have to invest is if everyone does their own setup, like we saw examples of HDR, of PSI, of ESRF, it's probably the most expensive option because we're all duplicating everything. And well, we have to have local copies of it. It has its advantages. Of course, you can choose your own metadata catalog, but you also have to have people to maintain it. Completely centralized would probably be the most cost efficient, but it's not also the one that people, it means also paying money to a central site or to a central place. This is an option which could also be considered. I think maybe seeing if one can use a centralized site like Zenodo and then having a tailored portal. But at the moment, the majority of people went for either local implementation or hybrid implementation. And I would be interested to hear if this is something from the facilities point of view, if they have a strong feeling about these or not. I think the actions we now have to look at is we have to get more funding via probably EOSC, because this data is going to be made available via EOSC, and I think the EOSC relies on having our data from RIs available. We're quite lucid, and we realize EU projects are not good sources of funding for operations, so we would have to fund the operations on our own. For this, we need leaps and lens, we'll see afterwards, to commit to something which is common, because now we have individual answers, but we don't actually know if collectively there is a strong commitment or not. And I think all of you, or most of you, are aware of there's quite a few national projects ongoing. Like in Germany, there's Daphne as part of NFDI. There's also the Helmholtz initiative. In France, there's the Sciences Ouvertes from the government, but being pushed by also French agencies. And I think working with these, they're also very happy to hear and see the progress that we make. I think for me, what's most important to keep the momentum going, having been part of these kind of efforts since the last 10, 20 years, PaN data started in 2000, I think. I see that every time the EU project ends, we actually have a break in the work that, there's sort of a break where people don't get together anymore. They don't, there's no networking, and then we get together again when there's a new proposal. I would be very happy if we could avoid that situation after PaNOSC and ExPaNDS, and we create a working group, I call it a working group dedicated to data management, to continue working on these efforts collectively and collaboratively. You can see from the presentations, yeah, that there is a lot of progress already in different facilities and lots of different levels of progress. And I think we can leverage that by working together. But of course, we have to commit, each facility that's part of this working group needs to have identified a data manager and also give them the necessary time and resources to contribute to this. So I think, you know, this is where I would like to see us going. And this is the question which is sort of open to our facilities and to ourselves, if we can pull this off after 2022. And I would conclude by just saying that I think we are really achieving what we set out to do. The vision seems we have individual commitments. Now we have to see how can we sustain it, and how is there really a collective commitment as a community, or is it still just individual facilities? And I will stop there and to say thank you to everyone who has, of course, contributed to this, and for you for listening.
Thank you, Andy. You were perfectly on time, which is great. And I think that now we can move with the next presentation. That will be by Katerina Biscari, that is chair of LIPS. And Katerina, I invite you to share your screen for any slides.
Can you see
and start your presentation. I can see the slides, so all good.
Very good. Thank you for this invitation. And I was attending just the last few talks, and it's very interesting. And my talk is almost a complementation of what Andy has just shown, because of course you have many answers. I still don't have all the questions. No, you have many questions, and I still don't have all the answers. But let me just for those of you who are not who do not know what LIPS is, which I think is very few from if I look at the participants to this meeting. LIPS is the consortium which includes all the synchrotrons and FELs of Europe. The idea started in 2015. The real startup of LIPS was in 2017. And we are almost 20 facilities in 16 different institutions in 10 different countries. But of course, our users come from all Europe and also beyond Europe. We think our user community is more than 35,000 from Europe. We have up to 300 operating stations. Publications. I think the next time I will present this slide, I will include also how much data we produce per year, because I think this is an important number to put also when we talk of what is LIPS. And so our vision, our mission, do you see my slides?
There's no problem. There's a small problem. It seems to be zoomed in on only 2/3 of the slide. Can you somehow unzoom it?
I don't know.
That's better, I think. Eh? That's everything.
Yeah, now it's good.
Now it's good.
Yeah, now it's good.
Okay. So our vision is to be the catalyst for solving global challenges. And we are therefore focusing on some of the special challenges that the world is facing, but we are giving instruments to the researchers of all the fields. So this is a very important part of what LIPS does, because it covers all the aspect of research. And the voice of LIPS is powered by the fact that we are combining facilities, combining countries, combining different fields, as I was saying. And we are working now for what will be the strategy for the new European research area. We had, years ago, we had started with what would be our strategy for this decade, but now we are aiming at focusing on what will be the strategy for the future in what is developing as the new European research area. And our landscape is in fast evolution from the technological point of view, and thanks to the technical advancement, digitalization, open data, and open science. I have highlighted here open data and open science. This is a slide I showed in the last meeting of the plenary meeting we had last week. And open data and open science is among the first things we mention when we talk of LIPS. Of course, we are an instrument essential for the European industry. And as I mentioned before, we are open. We are offering our instruments, and when we talk of data, our data for free to the members of all Europe, not only to the 10 countries that where our facilities are hosted, but to whole Europe. And therefore, we are, even if most of our facilities, there are only 2 which are international, all the others are national facilities funded by national governments, we are truly international when we speak of our capacity and our usefulness. We are organized through, as usual, through a general assembly where all the directors of the facilities are represented, coordination board where all facilities are represented. They are coordinating all the work and the activities. We have associates, which is the Sesame Synchrotron. We have several partners. One of them is the newest one is the ESO, the European Synchrotron User Organization. It's a strategic partner. We have an R&D board which includes representatives from different technologies and parts of our activities. We have 2 strategy groups, one for storage rings and one for FLLs. And then we have working groups. One is dedicated to beamline technology, one to photon sources, and one in which many of you are included from the people I see in this meeting, and many of you are collaborating, is this working group 3 for information technology. Then we have the working group for industry, the one for users, and the one for education, training, and outreach. And we used to work under each of these working groups has its own projects, its own collaboration, but then there are transversal programs and activities where we create for short time task forces. For example, there was one dedicated to our relationship with ESO, which now has become a strategic partner, and other activities. And among some of the documents that you can find, if you go to our webpage, you will find several documents and information. There are the first ones when we started with the LIPS brochure in 2017, then the LIPS strategy the year after, the LIPS landscape, which was published in 2019, and which we are going to renovate now. There will be a new landscape document, more than one document, a full publication in one review next year, because as I said before, the landscape is really in evolution, in fast evolution. And then there are different position papers for the Horizon Europe missions, LIPS facilities fighting the COVID-19, battery roadmaps, and then the digital LIPS. And I will come later on what can be one of these papers in the future. I want to mention one important part, which is our commitment for inclusion, diversity, equity, and anti-discrimination. You can find also here on the webpage information on what are our activities, especially what LIPS facility are committed to. And we have seen before several in the previous talk some information on the data used for the COVID-19. The implication of all LIPS facility with the pandemic has been great from the very beginning. Almost all the facilities open quick access mode from the very beginning, even during the lockdown during spring last year, in order to provide the beam lines and the instruments to those researchers who were starting to understand what was the virus and its consequences on the health, and also in the vaccine, in producing the vaccines. So it has been a difficult moment for everybody in the world, but being in this community where we have been part of the solution, which is not yet complete, but is of course it has allowed to resume the activities, to resume to react the community, the economy. This is a real. It has been very, very positive for all the community, not only showing what we are useful for, but telling ourselves why we are doing what we are doing. And from these difficulties and from the challenges we got last year for the operation, because of course it was not only operating for COVID-19 research, but resuming as soon as possible all the activities for all the fields, we have learned from the challenges and from the instruments that we were developing, the tools that we were developing in a fast mode to give you service to the users, to increase the remote access, to increase to working with the mailing system, with users connected via Zoom. This has shown us that there is a lot of possibilities to be improved in the future when we will be fully in normality, but learning from what we have started developing. So there is the program Digital LIPS, which has developed into 3 pillars. One is dedicated to user service, another one to training, remote training, and another one for green operation. And we are collaborating with other research infrastructure, analytical research infrastructures. Last year, we did a meeting which was done in February last year. I think it was the last working meeting I attended for more than 1 year, where we, together with all the other analytical research infrastructure, we met in Brussels to discuss how we are serving the Horizon Europe missions. And that was a first meeting, and from that we decided to create this network of networks where there are LIPS and then LENS, eDream, the high magnetic fields, the protons, the ions, and the lasers. This network is meant especially to provide the information to present common projects to the European Commission calls, especially for those projects where you need the complementarity of different instruments. We also wrote a position paper on how ARIE is a resource for the missions, and then another position paper on how ARIE is a resource for viral and microbial threats. And as I said before, we are in LIPS, we are advancing in technology, especially in synchrotrons, where we are moving from the 3rd to the 4th generation. And also the FEL, the free electron laser technology, is going towards always faster and faster experiments. This means that with the increase of brilliance, with the faster detectors and faster experiments, this technological change implies a huge increase of the data production. So this is very clear to everybody. I can quote someone saying synchrotrons, and especially synchrotrons in the past, were providing photons. Now synchrotrons are providing data to the users. And this happens not only in LIBS, but of course also with the other analytical facilities where this increase of the data production is clear and will be increased in the future. And to show how we are aware in LIBS of the key role of the data in all the facilities, I want to show you we had the last week plenary meeting, which was attended by some of you. There was only a one morning open session with the participation also of representatives of the European Commission and of the national funding agencies, and we choose to highlight only two key topics. One, of course, was our participation in the research for the COVID, and the second one was data management. And we had very inspiring talks by Andy, Patrick, and Vincent on this one on data management and the future of expanding PaNOSC, and another one showing what was also shown today, the example of ESRF and this human organ atlas. So this is just to show how key we consider that our involvement in managing the data in the right way is now. So on the data, we have been cooperating with LENS, what now is LENS. Before we were called LIBS and LENS, there was already a strong collaboration because neutrons and photons and X-rays were always working together in the field of how to deal with the data production and the data analysis. And this is the history. Maybe during this meeting you have been already seeing this slide, because I have taken slides from your talks, of course. But what is important is that what was at the beginning one program, it has increased, and it is now one of the most important activities in cooperation. And this also maybe you have already shown, but just to mention what are the facilities from LIBS and LENS which are involved in PaNOSC and ExPaNDS. So of course, most of our facilities are actively participating in these programs. I will not go here because already Andy showed and commented the results. Just to mention that it was done in the latest moment, and the fact that there are some missing lines doesn't mean that facility is not interested. It just means that it has not had the time to fill up, because what I can say from as LIBS chair is that all the facilities are aware and are interested, and you will get probably these tables filled up in the next weeks. And I also want to, here I take again some slides that were shown during the plenary last week, where you addressed us directly from what you need from LIBS and LENS partners, and it was mentioned this data steward, and we are considering this. All these suggestions we have been taking note. I will not, of course, answer now if this will be all put in place or not, but what is clear is that we are taking note of all the things, all the message that you sent to us about this teaching and learning platform, AI, data management, and so on. And also, you say LIPS data should be getting more attention. This is a message well taken, but I can assure you that the fact that LIPS data is one of the most important part and components of our technology for our environment is clear to everybody. So just to summarize, this complements what Andy has already shown, but to these questions you gave us, there are still mixed answers. There are some which are totally endorsing the idea of having this open data portal. Most are in favor of combined common and individual portals. Of course, each of us has to report to a different funding agency, so we have also to consider that each facility in LIPS has to deal with the national legal issues, with what the national funding agencies ask for or allow for. So this is something that when putting everything together, we have to, there are always some if not difficulties, we have to take into account the different conditions for each of the facilities. As I said, some are worried by legal issues. Then about the LIPS strategy paper on open science data, of course, in general, all are positive comments. One has to clarify who can give the support and the strategy and what we want to do in this paper, but this is something that is very well taken, and we will discuss about this. Then most of the facilities have interest in adopting the outcome of the two projects discussed in this meeting. Some have already adopted some of the tools or are in the process to adopting them. And the tools which are considered more useful are the Fair Data Policy, the DMPS, Nexus, HDF5. I read it because if you ask me exactly what it means, I will not be able to answer. Now, of course, DOE is, yes, we had before, and the open data. They almost all of us share the vision of a common open data portal. As I said before, there may be difficulties because of legal status, but I think this also is something that as we are proceeding in this evolution through the open data, and thanks also to the full commitment of the European Commission, also the national agencies will surely evolve and be more open whenever there is something, some difficult legal status. I think it can be solved in the future. So we are debating.
You have 1 minute or two left, Katerina.
Okay, I am almost finishing. I mean, this is my last slide. So what I want to mention is that it was mentioned also by Andy. Now PaNOSC and ExPaNDS will finish, and then we are almost sure that there will be another project, possibly in the work program 23 on. If there is a gap, LIPS is interested to fill up that gap with some internal project. The details are not yet defined, but we are in. We will discuss. We will have on the 26th of November a general assembly where there will be all the facilities. Finally, hopefully, will be face to face, and the data strategy is in the agenda. So all these questions will be after this general assembly. You will get more answers. But it's important that we are really committed in working on this, because it's important for our future. And this is my last message to you. Thanks.
Thank you very much, Katerina. That's great. And now we will continue with the next presentation by Robert McGreevy, that is the chair of LEMS. So, Katerina, I invite you to stop sharing your screen. So then Robert can start his presentation and sharing any slides. Robert, are you there? You are muted.
Yeah.
Okay.
Okay.
Yeah, we don't see the presentation view. We see as well. Now we see it perfectly.
Yep. Okay.
Wonderful. Go ahead.
So I wouldn't normally do this. I mean, the remit of this talk was slightly strange. So I've actually been writing my talk largely as the presentations went on and the questions came up. So a slightly different view from Katerina, and I probably have more questions than answers for you. But so this is a sort of live thing. So just first of all, to give the context of LENS members without a map, but to make a point about the different types of members we have here. I mean, all of the LEAPS members, as far as I'm aware, are operational facilities. It's not quite the same with LENS. So in LENS, we have 2 European facilities, and I put down that those are standalone legal entities. They can decide what they do about various things by themselves. We have national facilities, which are all part of another legal entity. And so they have constraints, if you like, from that. And then we now have what we call Neutron knowledge centers, which are organizations that used to run facilities, but no longer do, and partly run instruments at other facilities and have Neutron expertise there. So it's a very different sort of makeup in general to LEAPS in that context, but the different contexts are quite important for data. In terms of the structure of activities within LENS, and I was assuming you would know what LENS was, we have 2 technical working groups, one of which is the hardware instrumentation side, and the other which is the software and data side, which is working group 4. And within that working group, we have 7 different subtopics or subprojects, which are listed here. And I just indicated that I've ordered them in a sense that the top sets largely correspond to the activities that are taking place in PaNOSC and ExPaNDS, and the bottom set more correspond to the activities that are proposed in this new DITARI proposal, which was briefly mentioned in one of Katerina's slides. That's around digital twins to do with neutron and photon sources. So the fact that we have those sub-projects is no coincidence, of course, because the facilities have been working within these projects, and therefore, to a certain extent, we structure ourselves around the existing collaborations that we already have. I have some questions on, so one of the questions is on sustainability. Okay, so some of my questions are, what does sustainability mean, for example, finishing and implementing what has already been started, because although the PaNOSC and ExPaNDS projects in principle should finish everything, in practice, of course, there's always loose ends left off. Then there's simply maintaining those existing services, right? So you provide those services and they will require maintenance if they're going to exist in the future, and that requires resources. It's maintenance is not the most exciting thing, but it is somewhat necessary. And then, of course, there is further development of those services, of additional services on top of that. And presumably you do these things in that particular order, but we don't always. Sometimes we start developing new things before we finished things that we were doing before, right? Because new opportunities come on. But we've got to say, what does this sustainability mean? Because that's what you're asking for resources for. But secondly, you also have to look back and not just say, oh, well, we started doing this, so we're just going to carry on doing it. But, you know, you do have to ask yourselves the question, why does this need to be sustained? So are the things we have been doing deliver what we need or what we want? And for me, very particularly, what is the long-term goal? It still seems to me we're slightly looking at what do we do in the next 3-year project, not where do we want to be in 10 years in these terms. And I think we have to have much, for the data aspects, we really have to have this long-term goal and make sure we get towards it rather than just take these very short-term steps. So opportunities, these 2 things may not come across to you as opportunities, but I take them as opportunities. So the pandemic was definitely an opportunity. And for example, in the last case study by Frank, that was a very good demonstration of this, that the pandemic forced us to develop and implement things we wouldn't have done quite so quickly. So for example, like remote access to beamlines and so on, and more open access to data. And okay, we didn't actually do that immediately because in fact it was based on several years of pre-preparation, if you like, but we did it an awful lot faster in a few months than we would otherwise have done. So that actually just shows in these areas what we can do given the resources. And both of those are just like the vaccines, right? So there's really no difference. So at one level that says if we want to make progress on many of these data related issues, the resources really determine, of course, how fast we can go. And if we have the relevant resources, we can move pretty fast if we want to. The technologies are all there. We just need to implement them. So that I think is a fairly important message back for facilities, is that you're not limited by the technology availability, you're limited by the implementation of those technologies, just to do with the resources. Nobody, I'm surprised, has mentioned climate change or anything to do with sustainability in that context. This will be a very important feature of any of the things we decide to do at facilities in the next year, 10 years, 20 years. And we really have to think about this in the context of the data that's been being talked about now and the things we do with it. So all steps in the data value chain use energy. We spend, for Neutron and Photon facilities particularly, we spend an awful lot of energy measuring the data, right, and producing it. These very large data volumes that have been talked about, okay, we're going to store them somewhere. Great giant data centers, the energy used by those data centers is now comparable to the energy used by the facilities. It's not trivial. And so we really have to think about, why are we storing this data? Are we storing it that nobody's ever going to look at it, or are we actually going to make effective use of it? Analysis at one level that may not use up so much of the energy, but actually with more use of supercomputing and doing modeling in conjunction with the experiments we do, that's also very energy intensive. And then there's the end exploitation. So actually the access to the data, what are we doing with it down the line? So we have to think of all those things and how do they add up, and how do we actually get the best scientific output from that energy we're using. So it's no longer just about saying we're going to do all of these things because it's fun to do them. We really have to think about optimization in that whole data value chain. So that has to be a future goal of what you're thinking about. And slightly bizarrely, it might mean that you decide to run your facilities less and analyze your data more. And for most facilities, that's probably a heretical thing to say. But if you can't have all the resources you want, that might be what you have to do. So that's opportunities. Some of the challenges. So we've just had the discussion about common services, whether we do services in common or not. I mean, certainly the individual research infrastructures may be being asked to standardize with multiple organizations. They can standardize with Lens or with Leaps, or they can standardize with their host organization. Legal things have been mentioned. So that's a challenge. And that may not mean that you can't standardize in a way, but it just may mean you have to think about how you do it. And it's because the requirements are often similar, but they're not identical. So we shouldn't get too hung up on the, on what you might call the punctuation in the sentence. We should say, what are the basic principles we're trying to do here, and see if we can work around those. So we have to be pragmatic about these things rather than being dogmatic about it. But I would say truly common services, so you're talking about having a common data portal, are difficult. You have to have governance around it. You particularly have to have commitment. And I would say I'm not sure it's terribly realistic to think that everybody is going to finance some centralized service and then they're going to carry on financing it gaily for the next 20 years and be dependent on it. Facilities budgets go up and down. And what would you do about a facility who has decided to commit to something but then wants you to carry on hosting their data but not paying for it, for example? These things will happen. So I think the truly common services are actually really quite difficult. And in practical terms, you have to have interoperable federated services way more here. Common projects. So we have to think about budget and schedule. Times are tough, right? We all know budget's going to be tough for research infrastructures in the years coming because of the results of the pandemic and so on. And for a lot of facilities, making things to do with data a priority is going to be difficult, right? It doesn't necessarily have the highest priority. And as I said, understanding whether you're going to operate your facility or use the data more effectively, that's a big challenge for any facility director to come across. And the first thing would be to say, oh, I will operate my facility and I'll deal with the data later. So it's going to be difficult, and therefore the case for investment is going to have to be very strongly made. We have been, over the last years, very dependent in a sense on EU projects for defining for us a timetable, a schedule, a budget, a process for working together. I think particularly in Horizon Europe, it's fairly clear those opportunities are less than they were in the past. And we really need to understand how we define common projects and finance them and run them for ourselves, and not just carry on being dependent on the EU opportunities that arise. Because otherwise we're not setting our own strategy, we're actually being dependent on somebody else's strategy, which may not be the highest priority. And in the end, the facilities actually end up paying most of the budget for these things anyway, right? It's not the EU that provides most of the funding. So in the context of EOSC, I mean, EOSC is setting the direction of travel, which I think is good, but it's not paying for most of the journey. And so we've got to be very clear that it's not just about being in there, but that it's delivering the things we need to be delivered with a high priority. With regard to fair data, so Frank said he liked, and it wasn't Frank, so Patrick said at the beginning that he liked rules. I'd actually read that fair for me is an aspiration. It's not a rule or a law. And all data are not equal. So we've been kind of discussing as if every single data should be equally subscribed to all fair principles. I'm not sure that's actually right. We have so much data of so many different sorts, we are going to have to prioritize. And if you try and do everything equally, you will end up doing not anything very well. So a few conclusions. I think very firmly that neutrons and photons should continue to collaborate. We've been doing this for a long time, and there's been a lot of benefits to it. The facilities work in very, very similar ways, and having similar thought processes is actually very valuable. And I would make the point, and I think that's kind of came in some of the stuff that Andy said, continuing to collaborate involves people. Collaborations involve people. And if we stop collaborating for a while, you lose those personal links, and you actually then have to reinvent all that. And that's very expensive to do. So continuing to collaborate, even at a lower level, is really, really critical. But obviously not all facilities can proceed at the same rate. They don't all have the same funding. And sometimes, even if people aren't involved in the development, we have to recognize that implementing things that exist do require resources. You can't implement something for free, not the sort of things we're talking about here. And we tend to forget that. We tend to just think, oh, we've developed it, somebody else can implement it. So we need to look at priorities. So as I said, not just to say, well, this is what we've done in ExPaNDS and PaNOSC, so we just carry on, but say, okay, let's look at those things and reset them where necessary. There are differences between the neutrons and photons. We do not have the data volume problem that the photons have and are certainly going to have with the fourth generation synchrotrons. And that may mean some slight difference in priorities in terms of where you deal with things. But I still think there's enough overlap to make it beneficial to carry on collaborating. Strange sentence here, democracy may not be the best way of setting priorities. From a person in the UK, you might understand why I think that's not necessarily the best solution. What I mean here is that it's all very, it's all very well doing surveys and saying what's everyone going to implement and so on. You can end up with everybody agreeing to do the lowest common denominator, which is the thing that's easiest and cheapest, but it's not necessarily the highest priority. And for some of these things, you need to have single facilities or small groups who will say, we will take a lead here and we will make the running, not that everybody has to equally agree about everything, because that's the practical way things are actually going to happen. And one of the things that slightly bothered me from some of the presentations in the meeting was it's slightly focused on the technique and not the science. So the particular photon technique or neutron technique, etc., from the beamline perspective, I'm not saying what area of science does this sit in. And our data only has value in those broader areas of science, whether it's physics or biology or whatever it is. It doesn't have value just as a neutron or synchrotron technique. That's much too inward looking. So I think we have to think about our data in the broader scientific context, not just in the neutron photon context. Just going back a bit, so I actually just looked up during the meeting. So I wrote the original ISIS open data policy in 2005, at which time our users were adamantly opposed to any possible idea that their data should be made open. And I distinctly remember a meeting roughly 10 years later where they were all arguing that absolutely, how can you possibly think data is not open? So in order to see the value in some of the things we're doing, you need to change some of the culture, right? There's some areas of science where the open data, all aspects of open data are really totally accepted and we use them all the time. And there are other areas where people are still keep their stuff to themselves and are very concerned about what I call the risks in making their data open. So they need to see the value. And so sometimes that means the facilities have to be a step ahead. You can't just follow the users. Sometimes you actually have to be ahead of the users. But certainly I'm a bit, we're still discussing data policy for what I call raw data just produced by facilities. You know, again, 15 years after some of these things were first developed. We just need to get that done and move on, really, and not discuss about the grammar and the punctuation, but we have the basic principles. And I think the FAIR data principles are helping there. But I said in relation to FAIR that I think that the F and the A bit is, findable and accessible is applicable to all data. I think, if you can't find the data, it doesn't have any value at all. But the IR bits is where we really have to think, how much effort are we going to put into particular bits of data? I don't think all data are equally interoperable or reusable. And so I think we do have to have some thought there rather than just applying these principles in a blanket way. I'm not entirely sure. Data management plans are maybe useful and they may be useless. I think in lots of contexts, they're just used as a way of satisfying somebody that you're doing something about data, but they're not particularly meaningful. And in a way, I don't think there should be data management plans provided by users. This is what we're going to do with our data. I think the facilities, we should be saying, this is what you are going to do with your data, right? So it's that's swapping it the other way around. I'm a strong believer that the real value lies in what I will call published data. The most of the raw data we produce in facilities is not really reusable by other people, except in very, very small contexts. Things like the MX and so on is very different because it's a standardized sort of measurement. But a lot of our measurements, it's a real experiment. People are changing stuff as it goes on. The idea that you are actually capturing all the metadata from that on an ongoing basis is probably not realistic. And we don't really concentrate on, having a data policy on published data is much, much more complicated, because usually that is only partly from the facility, it's partly from other experiments, etc. But that's where the value is, and that I think is what we have to work on, is how we're actually going to get hold of that data. And again, put it into databases. We had very little talk during this meeting about the case studies are single case studies. I did this experiment, I can make my data from this single experiment available. That's not usually where large value lies. Large value lies is in databases of hundreds and thousands of such experiments, and you can get the data and then start to analyze the whole thing. And we're not largely thinking along those lines, that we've got to make this routine, and we've got to make massive databases of all the information we're producing, not just single case studies.
1 minute.
I like the comment about who is the audience. That was the same thing about me saying where does the value lie. So who actually are we addressing in this area? And I think again we have to think about it and not just apply the principles willy-nilly. And as I said, optimizing energy use as a data value chain is absolutely going to be one of the major drivers in the next 10 or 20 years, and we've got to start putting that into the proposals. So my conclusion is not really this is the answer. Actually, what I'd like to see is the PaNOSC and ExPaNDS groups come and say, okay, we've thought about all these things. Here's our proposal for what we should do in the next 10 years. That's what I'd really like to see. And then we can have something we can get behind.
Thank you very much, Robert. It was very, very interesting. And I think that now we will go to the last slot of the day. We will have Andy that will be managing questions and answers and discussions and just wrapping up today's symposium. So I don't know if we have any question that has not been answered from the question and answers tool, or if anyone wants to ask anything, but Andy, the floor is yours.
Yeah, I would just make a comment to kick off. Is first of all, thank you to both of our invited speakers who came up with very good feedback and also more work for us. I'd like to, I just to mention to those of you who are maybe new a bit in this area, that it's thanks also a lot to the efforts by Robert, who even if on one or two slides I thought you were quite, you were holding back or a bit negative about what we could achieve. I think some of the ideas we discussed 15, 20 years ago are far advanced, and we're getting close to, I remember in one of the proposals, we said we'd have a Google map of neutron and photon electron distribution. So, you know, different data from different sources, and we'd make a map and we'd combine these data sets. I think this is happening on an individual level already, but we can actually make it happen on a larger scale. I take the message also that you, so you were, part of your dream is actually coming true. I think part of your predictions or list of wish list. I take a message from Robert as well, saying we should be thinking even bigger, maybe, you know, I mean, if you say we should go towards databases and things like that, we didn't address that. We first tried to make the data open and fair, because today there's still too many facilities that are not that haven't implemented that yet. So I think we are advancing, but I would really like this to continue, because I think the community is very, as Katarina said, it's got very important data to share and to give back to science, and actually making it, I mean, my firm conviction is giving it a common home would increase the visibility of the whole community. It would be it would mean even more than just websites. You know, people today, we have our websites with news of this result, this publication, but actually having a web home where we can find lots of data, I think is actually something which would give us a foot into the door of what I call, you know, when you see what CERN is doing, when you see what the life sciences are doing, they are present, because more present than us, because their data is actually being presented together. Yeah. So that was just a feeling I had. Yeah. Okay. I don't know if you want to say anything to that, Robert.
But that was exactly what I just said, right? It's. I mean, you're thinking about the data together in the sense of, okay, it's the data coming out of neutron or photon facilities together, but actually it's even bigger than that, because then you said against the life sciences, the life sciences are not having a single technique hidden over in a corner over here, right? It's actually, you know, it's multiple techniques, right? And you put all the data together. So yes, absolutely, the visibility. I mean, that's not the same thing as saying that you have to have a single external thing that you fund to produce that, right? I mean, you can do that in different ways.
Yes. That I also agree to. We need to find a way of achieving that with minimal effort, you know, and also minimal funding, because I think a lot of the bricks are there. What we want to do is make it, just bring it together in a way you often do, just with a very light layer on top. I don't know if anyone, Patrick, you want to say something?
I would like to refer to one of Robert's remarks. Not the one you think right now. It's another one. It is you criticized a little bit the timeline of the European Commission, because you said we should focus on the facility timelines first, and then not allow the EU Commission to dictate us where we go. But I can't speak for the Commission, and I see we only have one from the Commission here with us. So I think what we should focus on is to elaborate a little bit more what our timeline is and to make this known to the Commission, like having white papers and having policy papers. They ask us, yeah, they really want to know what our goal is. They're not imposing something because they have nothing else to do. It's just that they watch us through a keyhole, and from that they try to find out what we actually want. Yeah, so I think it's fair enough to say that we should put more effort into contacting them and making clear they understand what our timeline is, because they really want to help us. Yeah, it's not a fun game or something.
No, I mean, I didn't. I sort of said priority rather than timeline, but
okay, yeah.
We are at the moment sitting slightly in a situation that's not just to do with the data side, it's to do with Horizon Europe has changed the way that things are being funded. Not so much in the things like the EOSC area, but certainly in other areas. And we're slightly sitting around saying this doesn't really fit with what we do, but it's dominating our thought process. It must not dominate our thought process. It's one of the tools we have is European Commission funding, but we have other tools.
Yeah.
And if we let it dominate us, we won't make decisions for ourselves.
I just want to say that it's a little bit on us, on how we influence future funding programs.
No, absolutely, it's on us. Yes.
And especially in the years as we have the association, we can become member and we can try to steer this. I mean, it's getting big now, so it's getting more and more difficult to get our science in there. But we have the tools, I must add. And I'm, of course, as you said, I'm really disappointed by some of your remarks. You are right that data is different, but the fair data principles, from my perspective, is they're more a way of handling the data. And if you refer to MX data as being different because it has standards and so forth, isn't it that we could make most of the data the same way and that it can be reused? If an experiment is made and no one else can read the data, it cannot even be verified anymore. Yeah.
If you pick off all of the data types that are produced by neutron and photon sources and you try to implement all of those processes equally at the same time, you will never finish anything.
Yeah.
So you have to make choices. And so therefore you have to say this set of data is, maybe it's easier to deal with, maybe it's more important to deal with. We'll do this one and we'll do it properly, and then we'll do that one. But we will not have the resources to do everything equally all at the same time.
Absolutely. But maybe you should see the positive part. I think I'm echoing something Darren was just chatting with me, is that at least now we have some kind of vocabulary where we can classify, which we can use to classify what we can do well and what right now is missing. In the past, I mean, all those terms didn't exist and we were just like struggling with making things open. And now we have the vocabulary to do that. I agree that you cannot do this with all the bits we are connecting.
Yeah, but I mean, I'm not against open data. As Andy will know, I've been pushing this for nearly 20 years.
Yeah.
But therefore, I want us to make progress, and we only make progress by setting priorities. We don't go make progress by, and we do need to set priorities here. And again, facilities are not going to individually fund these things unless there are very clear priorities, which they have to weight off against other priorities. That's the reality of facility management.
Yes, of course. But I have to fight for this fair data. Yeah, it's
absolutely,
my job.
Absolutely. And I'm pushing you to do so. Please fight for it.
And I also sign up, I mean, to both comments. I mean, I know also from our scientists that some of the data they declare, the raw data, as being quasi unusable, a lot of it, yeah? And they know that themselves because they were the authors of it. But there's other useful data in that, and I see already the fact that we address this, at least at ESRF, people who are developing new algorithms or people who need to have test data can now go and find it in the open data. Whereas if you speak to most of the software developers, they were saying it's a fight to find data sets which are examples of, and these things we solve by addressing all of the data and not being too picky around it. But I also agree with Robert that if you have difficulties achieving it for all data, you should start with the most important data, which is published data. Yeah? And that should be the minimum objective of all our facilities, that all publications can provide the raw data for that publication. which is a small subset of what we produce, a very small subset. I'm also very happy to hear from Katerina that we will have this topic will be on the LEAPS agenda. So if there's any information, and I also appreciate, I don't know if he could be here today, but the support we got from Gaston last week, and I think this is very beneficial to this topic. Yeah.
Yes, of course, it is there because we are aware of the importance, as I said, of this topic in all our activities, and we will discuss. Sure, we may come to you to ask for more information we need before the presentation, before this meeting.
Yeah, I don't know if you. I presume this is the same almost in all countries now, but I was last week also at a meeting of the French RDA. Antenna, and the French government is really pushing this open science, science ouverte, with lots of activities and even small funding, but also lots of tools, websites, all these things. And so I think there's something we should really leverage. Yeah?
Yes.
But I think we have the coordinator of Daphne, which is a large project in Germany. Yeah, so I don't know. Anton, do you want to say anything or not? No. Well, are there any other comments people want to make, or like, you know?
Hi, Andy. I was muted, and it seems like Sophie allows me to speak again. Yeah, we're lucky in that we've got a project that's just kicking up, and of course we have to coordinate with the PaNOSC ExPaNDS stuff, don't reinvent the wheel, and try to thinking of Robert's bit about prioritizing, kick the can a bit further down the road so we can get the most impact for the community and then move on.
Yeah, I think it's actually, I don't know if you agree also, Katarina and Robert, but it's part of it's something which every facility has to take into account as part of their operational, you know, of part of the operation. It's not something you only do when there's a project or something you only do if you feel like it. You now need, and this was one of the topics we made, every facility needs at least one data manager, I'd say.
Yes, I mean, most of the big facilities have, of course, data, you can call data steward, data manager, or whatever, but there is always someone dedicated to that at least in the LEAPS facility, as far as I know, apart from the very small ones who are not producing much data. And this is also something that is important also to have these people connected to share experience and to build together what will be the data manager, you know, of the future.
Yeah, we saw the difference with new facilities. Like you take Eli, with the fact that they were part of PaNOSC, and I think they got a huge boost from the beginning in terms of data management. It was taken seriously from the inception of the Eli Eric. Sorry, that's my cat. I have to move my cat.
He wants to have lunch. Sorry, I was talking to John Elliwell by the chat without seeing that I was also sharing with all the panelists. We are all friends.
Yeah, that's not a problem. Don't worry about that. Is there anyone that wants to raise the hand or has put any question, anything? Because we have still 4 minutes left and this cat is hungry. So
not only the cat.
Yeah.
John wants to talk.
Yeah.
I think John is raising his hand.
Thank you, Johnny. Yes. So just to touch base with the discussion with Frank von Delft there, and congratulations to Frank, so everybody hears it, on all they're doing with the moonshots. at Diamond there and all his worldwide collaborators. The reuse of raw data, Protein Data Bank Japan, which is who PDBJ is, have set up a raw data archive linked with PDBJ. And I learned about this at the PDB 50 celebrations in the summer, because he had the director Genji Kurisu had a poster about it, and immediately linked up with him and offered to help, basically being a data referee. And at RDA 17 plenary in the COVID session, we had this quite vigorous debate about the problem of reuse and the multiple versions of protein coordinates, and confusing thereby potentially the community that Frank alluded to, who are the non-crystallographers consuming the results of crystallography. And so by adopting the model of a journal, the referee feeds the editor in the journal with advice. And basically, me and my helpers, we're doing the same for PDBJ, and then they contact the depositor. So this connects actually with Bob's point, and I agree with Bob's point about the big challenge of boiling the ocean, to use a common analogy. So within IUCR Committee on Data, what we've done with our report on the opportunities for raw data archiving, which are absolutely monumental and phenomenal new opportunities, the individual commissions are now debating what those opportunities mean for them individually. So the macromolecular crystallographers have gone in wholesale. There are now journal defined policy requirements for connecting raw data with article. But the chemical crystallographers, the structural chemists, are still debating quite how far they want to push it. Likewise, the powder diffractionists are debating how far they want to push it. And this is really a very interesting mixed landscape. The overarching point that I think needs to be made at some point is that I think it's the funding agencies that, to me, are pushing the open access to raw data of unpublished data, because they suspect, I'm guessing, that it's actually, there could be more published data, published results from measured data, because they suspect that there are major inefficiencies in the user community across all boards. So what is the fraction of our data that leads to publication on the one hand, or the possibility of database deposition, which is a form of publication? But personally, as a researcher, I don't like the idea of my lab's data being released openly after 3 years. Some stuff is difficult to analyze, and I come back to it time and time again. I never abandon it. So in that sense, preservation of data, even when not published, is important, but I don't want it to be open. Anyway, there's rather quite a concatenation of points there, but I hope they resonate with the different things that have been made through the whole session, which I found absolutely excellent. Thank you very much, guys.
No, and I could just add, John, that we are helping you, the IUCR, with the new journal to verify raw data and the metadata.
Absolutely. We have a new initiative in the IUCR journal's raw data letters, because there are instances where multiple lattices are not analyzed. Only the primary lattice is analyzed by the crystallographer and publishes that. That there's much, much more we can do with the raw data, including not only structure, but also dynamics of structures.
And this is thanks to Fabio from EUXL, and of course you and all your colleagues here. So yes, I think what we've achieved now, we've got to the deadline where lunch is probably, the canteens are closing. So I don't want to be the cause of your hunger, but I just want to say I really enjoyed the talks as well. The quality of the talks I found was very good, and it's very interesting to see use cases. It's more interesting than seeing use cases than Gantt charts, at least for me. So I enjoyed today's symposium a lot, and I look forward to hearing more from the General Assembly of LEAPS, and we will take up Robert's challenge to make a proposal. It's easy, well, not easy, but we can make a proposal. We're very motivated, yeah. And thank you everyone, local organizing committee, Kat, Jordi, Sophie, Patrick, my co-equipier. And thanks everyone, yeah.
All right, thank you very much, Andy. And I reiterate the thanks to everybody that helped organize this event, everybody that participated, all the people that make questions. Thank you very much to all of you. And we keep in touch because PaNOSC and ExPaNDS, they still have a little bit of time to run, and we will deliver more and we will catch up again. Thank you very much, everybody.